Welcome to TQC 2021. Last year, we were hoping that in 2021 we would meet in Latvia in person. Unfortunately, the pandemic is continuing, so we are organizing the second online TQC in a row. However, holding conference online makes it easier to present talks, and we had a record interest from quantum computing community with 245 submissions this year. So we have an excellent program consisting of 4 invited talks by Cecilia Lancien, Srinivasan Arunachalam, Kaimin Chang, and Scott Aronson, 78 contributed talks selected by program committee from this record number of submissions, 2 poster sessions, and this year as an experiment we are also having 2 open problem sessions in which everyone will be able to share their favorite open problems. So enjoy the program, and I hope this leads to many new ideas and insights for the TQC participants.
Okay, so also very warm welcome from my side. I'm going to be the host of this first session, and it's going to be my pleasure to host Cecilia Lassien for the first invited talk. Cecilia was my co-PhD student back in Barcelona and has since very successfully moved on after a stop in Madrid to now be a CNRS researcher in Toulouse. And she will tell us about typical correlations and entanglement and random MPS and PAPS. And before we start, I want to remind everyone that you can use the Q&A feature in Zoom here to ask questions. And we can also at the end unmute some of you if you raise your hand after the talk for questions. And with that, I would like to give it to Cecilia, and yeah, please go ahead.
Thanks a lot, Christoph, for the introduction. So let me just share my slides. Okay, do you all see it well?
Yeah, I think it looks
okay
good.
Yeah, so yeah, I'd like to really thank everyone who was contributed to putting together this conference. I mean, the steering committee, the program committee, the local organizers having to adapt once again to the ongoing pandemic. I mean, I'm really honored to being this talk at TQC 2021. I mean, if I have to be fully honest, I'd even say I'm a bit stressed out of having to actually give the opening talk of this conference. But well, at least in 1 hour, I mean, this is done, and I can enjoy the rest of the program in a fully relaxed way. So that's probably for the best. So what I'm going to tell you about today, the goal of this talk is going to be to try and understand what are the typical properties of matrix product states and projected entangled pair states, and in particular, trying to understand what are their typical amount of correlations and entanglement. So this talk will be mostly based on some joint work with David Perez Garcia, which actually the first version of this work was already out 2 years ago. So it is getting a bit oldish, if you want, but it's still something that I'm working on at the moment. So at least in my mind, it's still fresh and active. And hopefully I have time at the end to tell you a bit about more like work in progress aspects, and in particular the entanglement aspect of this title. And also it's something that I don't think any of us presented at a big conference, so I thought it could be the opportunity to present this to a broader audience. Okay, well then let's get started with a bit of background and motivations around this topic. So, I mean, as you all know, when you're dealing with many-body quantum systems, like the main problem is what people often call the curse of dimensionality, namely that if you have a system which is composed of n d-dimensional subsystems, then this global system has dimension d to the n, which is exponential in the number of subsystems that are involved. And this dimension becomes like remakes any kind of computation intractable as soon as more than a few subsystems are involved. However, it's also known that in several contexts, the the states of such many-body quantum system, which are actually physically relevant, and I will come back on the next slide on what I mean more precisely by this. So these physically relevant states are well approximated by a much smaller subset of this global exponentially large state space, and namely the subset of so-called tensor network states. So let me explain to you what are these tensor network states. I mean, I apologize for all the people in the audience who know this very well, but I mean, I somehow have to assume that some amongst you don't know what tensor network states are. So, okay, so if you want to construct a tensor network state on CD tensor n, so the way you do it is that you're going to start from some underlying graph G, which has n vertices and some number L of edges between them. So here you have an example drawn with 6 vertices and 7 edges. And then what you're going to do is that you're going to put at each vertex V of your graph a tensor that I denote chi V, and this tensor will have 2 types of legs. So it will have one d-dimensional leg, and this d-dimensional legs will be called the physical legs. And then it will also have some q-dimensional legs, and the number of such q-dimensional legs, which are called the bond legs, is going to be the degree at your vertex V, so the number of edges at your vertex V. So I have represented this here. I mean, if you don't really like this diagram notation for tensors, I mean, don't worry. In the rest of the talk, I will always also write things with indices so that everyone can choose the representation that they prefer. So, okay, here, that's what I represented. And this q-dimensional legs in gray and this brown, like d-dimensional legs in brown. So in this way, you get this big tensor, chi tilde g, which lives in n copies of CD, tensorized with 2L copies of CQ. And then what you do in the last step is that you're going to contract together the indices of this tensor chi tilde g, which are associated to a same edge. So I represent this tensor, this index contraction by merging together the corresponding legs. And in this way, what you get is a tensor, chi G, that lives in CD tensor n, so in your physical space, CD tensor n. And this tensor, up to renormalizing its norm, is going to be a pure state on CD tensor n. So what's the interest of this whole construction? Well, if you have a graph which is somehow reasonable, where the degree at each of your vertices is upper bounded by some parameter r, say independent of n, or then this state will be described by a number of parameters, which is at most n times q to the r times d, which if this parameter q is also fixed, then you have a quantity which is linear rather than exponential in n, okay? And just like one thing I should say now, so I've described this like very general construction of tensor network states. In fact, in this talk, we're going to be only looking at the like really simplest cases of such underlying graph G, namely when your graph G is a regular lattice in dimension 1 or 2, so a line or a rectangular grid. And in this case, we will call the resulting tensor chi G a matrix product state in dimension 1 and a projected entangled pair state in dimension 2. Okay, so now that I've described this like class of state that we will be looking at, let me try to come back a bit on the like what are the kind of physical state that this tensor network state are supposed to represent. So if you want, ideally, a tensor network state representation is supposed to be a mathematically tractable way of describing the state of a system, which is composed of many subsystems that have a certain geometry, which is represented by this underlying graph G, and that are subject to interaction that somehow respect this geometry. You have to think of the interaction as being mediated by the edges of this graph. And maybe like the most important example of like where this correspondence has been really rigorously proven is the following. So it's like really proven in some cases, conjectured in some others, that being a tensor network state with a small bond dimension q is approximately equivalent to being the ground state of a gapped local Hamiltonian. And just a few comments of like on the vocabulary. So what I mean by local Hamiltonian is a Hamiltonian which is composed of terms that act non-trivially only on nearby sites inside this graph. And being gapped mean that you have a spectral gap between your ground state energy and your first excited energy, which is lower bounded by a constant independent of n, so that the spectral gap doesn't close to 0 as n grows. So that's a really important like equivalence between these two families of states. and which is constantly used in practice in condensed matter physics. Like, so you use tensor network states as ansatz in computations, which allows you, like, if you want to estimate the ground state energy of such a gapped local Hamiltonian, to perform an optimization over the subset of tensor network state, meaning over a manageable number of parameters, even for large n. And this really brings us to maybe the general question that motivated our work at the beginning with David. It's like what are the, like amongst all these various qualitative intuitions that physicists have about tensor network states, which ones are true, if not always, at least generically? And in addition, in this, like when you're looking at this generic case, can you make more quantitative statements about what's going on? And maybe like one very natural way of trying to answer this question is to, well, sample tensor network states at random and try to study what are the characteristics that these random tensor network states will exhibit with high probability. And in particular, what is going to be their typical amount of correlations or the typical amount of entanglement, okay? And maybe one thing I should say already now is that in everything that I will tell you about, the regime that we are really interested in is the one where both this physical dimension D and this bond dimension Q are large. That's the regime where the results will actually be interesting. And ideally, we'd like these results to be valid for any n, so that they remain true in the thermodynamic limit where n goes to infinity. Okay. So I guess that's it for the general motivations. So now what I would like to do is to really present to you like more precisely what are the models of random MPS and PEPs that we looked at, what were precisely the question that we asked, and to summarize in like just one slide what were the main results before we go into more details. Okay, so let's start with the one-dimensional case. So like trying to construct a random MPS. So in this case, so like just to repeat what I've said before. So in this case, your underlying graph G is just a line. So you have your n particles on the line. In this talk, I will impose some periodic boundary conditions. I mean, it's really not so important for the results, but just to fix ideas. So these particles are actually going to be on a circle, like you have to join together the first and last one. And then, well, you have to pick at random your one-side tensor. So your one-side tensor in this case is going to be a tensor chi that lives in CD tensorized with 2 copies of CQ. There are 2 outgoing edges at each vertex. And we're going to sample it in the simplest possible way you can think of, namely as a Gaussian tensor. So its entries are going to be independent complex Gaussians with mean 0 and variance 1 over dq. So this choice of variance may seem a bit awkward. I mean, it's just the one that you need to impose if you want that at the end of the construction, the resulting tensor that you get will have a norm that will be with high probability very close to 1, and which somehow like the state will be already with high probability close to being a real state, and you don't have to worry too much about normalization issues. And in this talk, indeed, I will really forget about this subtlety that maybe the tensor is not exactly normalized, but with high probability it is close to being normalized. Okay, so I've represented here this one-side tensor, written here with indices if you prefer to have this expression. And then what we would like to do is to construct a random MPS, which is translation invariant. So once we have sampled this one-side tensor, we will repeat it on all n sides. So not resample, but really repeat this same tensor, contract together all neighboring 2-dimensional indices. And in this way, you get the resulting object here, which is a random translation invariant MPS with periodic boundary condition. Okay, and one last object I have to introduce is what people call the transfer operator that is associated to this MPS. So the way you construct this operator, that you take your one-side tensor chi, you take its complex conjugate chi bar, and you contract them on their physical index. So in this way, you get a tensor in CQ tensor 4, and instead of viewing it as a vector, you actually view it as an operator from CQ tensor 2 to CQ tensor 2, which I've represented by adding some arrows here on the input and output legs. So again, you can write with indices what this transfer operator looks like. and in fact group terms together inside some matrices and see that you have this kind of compact expression for this transfer operator as an average of D terms, which are the form Gx tensor Gx bar, where these matrices Gx are independent Q times Q matrices whose entries are independent complex Gaussians with mean 0 and variance 1 over Q. So you have this, which is like, if you like random matrices, somehow it's a kind of neat expression for this random transfer operator as the sum of the like random Gaussian matrices that have this tensor product form. Okay, let's move on to the PEPS case. I mean, the construction is going to be entirely similar, so I will maybe go a bit faster on it. So this time you're on a two-dimensional grid, so you have m times n particles on this rectangular grid. Again, we will impose periodic boundary conditions in both directions. So these particles are actually going to be on a torus. You have to pick your one-side tensor, this time in CD tensorized with 4 copies of CQ. Again, we will pick it as being a Gaussian tensor with the correct variance, so that at the end of the construction, the resulting PEPs will be with high probability almost normalized to having norm 1. Again, so you contract everything, and in this way get random translation invariant PEPs in both directions with periodic boundary conditions. So here I've represented this one-side tensor, and here what I've represented is not the fully contracted PEPs, but only the tensor that you get if you contract along one column and leave the other indices free. So that's this one column tensor chi m that I've represented here. And why is this column tensor important? Well, because in this PEPs case, if you want to construct the associated transfer operator, you actually do it from this column tensor chi m. So you take chi m, its complex conjugate chi m bar, contract them on their m d-dimensional indices, and get this operator from CQ tensor CQ tensorized m times to itself. Okay, and again, if you want, you can write down an expression for this transfer operator in terms of some Gaussian matrices. So this time the expression, I mean, it looks like the NPS case, but it's a bit more nasty. And in particular, the subtlety here is that, so again, all these matrices GXIJs are independent from each other, but because of this PEP structure, a given matrix GXIJ might appear several times in the sum on different sites. And so it really makes this PEPs case more difficult to analyze than the NPS case, but we will come back on this later. Good. So now that we've introduced the models of random NPS and PEPs that we will be studying, let me tell you what is the question, like the main question that we will be asking. So what we want to understand is what is the amount of correlations inside these random NPS and PEPs. So when we talk about correlations, what we want to do is to like perform local observables on our NPS PEPs and try to understand, try to quantify what are the correlations between the outcomes of these local observables when they are performed on sites that are distant from each other. So in fact, what I will call the local observable, so in the NPS case, it's going to be an observable so that really acts on one site, so on CD. And the PEPs case, it's going to be a quasi-local observable, if you want, because it will be acting on one column. So it will be an observable on CD tensor M. Okay? And then, so more precisely, what I want to do is, so I want to compute on my tensor network state the following observable. So where I put observable A on site or column number 1, then some identities on the K following sites or columns, then observable B on site or column K plus 2, and then some identities on all the rest. So it's the following inner product that I want to compute, which I've represented down here in the NPS case. And what I want to do is to compare it to the product of the values of the two observables where I have either only A or only B. Okay, so these two quantities here. And what I will call like the amount of correlation in this tensor network chi, so between observables A and B separated by K sites or K column, is simply going to be the absolute value of the difference between these two quantities that I want to compare. And the question that we ask, so is that, okay, is it the case that when K grows, this amount of correlation goes to 0? So this, I mean, most probably yes. And if it does go to 0, at which speed? Okay. And now, so the intuition that people have is that, in fact, for any tensor network state, I mean, not just random ones, so for any tensor network state, you should observe a very fast decay of correlation. And in fact, you should observe an exponential decay of correlations with the distance that separates the two local observables. So the intuition that people have is that this correlation function, this gamma of A and B separated by k size, should be upper bounded by some constant c that depends on your tensor network state chi, and then this exponential factor, so this quantity that is exponentially small in the distance k that separates the two sides on the two columns, and then the operator norm of these observables that you can normalize to being at most 1. And what a bit of vocabulary, what people call the correlation length in a tensor network state is simply the inverse of this rate tau at which you observe this exponential decay of correlation. So this quantity here is 1 over tau. So that's, like, say, the general intuition. And if you want our result, like stated in a very, very informal way and really hiding a lot of limitations here and there, is that if you're looking at random translation invariant MPS and PEPs with periodic boundary conditions, so the models that I presented to you a few slides ago, then this intuition is generically true. What I mean by generically is that with probability going to 1, and in fact going to 1 exponentially fast as the parameters d and q grow. And in addition, what you can show something more quantitative, that it's generically true with a correlation length that you can prove is very short. And what I mean by short is that this correlation length actually goes to 0 in this regime where d and q are large. Okay, and so before I go into more details, let me give you a very brief summary of how we can prove this result. So we actually have two ways of proving this result, which, as we will see, are suited to different dimensional regimes. So one possible approach is to show that this transfer operator T that I've described to you is so this transfer operator associated to our random MPS or PEPs generically have a large spectral gap between its largest and second largest eigenvalues. What I mean by large in this case is that it goes to 1 when d and q grow. Okay, so I will tell you later like why having this large spectral gap implies this short correlation length, but so that's one way of approaching the question that we have. And the second approach is to show that the parent Hamiltonian of our random MPS and PEP, so I haven't properly defined this object yet, but I will when we come to this. So this parent Hamiltonian generically has a large spectral gap, this time between its smallest and second smallest eigenvalues. Okay, so that's really the two strategy that we have. So then in the rest of the talk, I will really present each of these approaches in more details, like tell you why they actually imply something about correlation length. But let's say if you want just like a take-home message for this talk, it's on this slide. And if you want more details, then you can continue following, but otherwise you can really just slack off and wait for the break. Okay, so let's start with the first approach. So trying to show that typically in our random MPS and PEPs, there is a short correlation length by showing that typically their associated transfer operator has a large spectral gap between its two largest eigenvalues. Okay, first let's try to understand how the spectrum of this transfer operator is related to the speed at which you observe this decay of correlation. So it's actually a very simple observation. So if you remember the diagrams that I had representing this like values, so the values of these observables, the one involving A and B, the one involving only A, the one involving only B. So before we were reading these diagrams, if you want, vertically and seeing them as inner products between our local observables and the tensor network state. And instead, if you read the diagrams horizontally, then you can see them as some traces of some powers of your transfer operator T intertwined by some operators A tilde and B tilde that you construct from your observables A and B in the way that is described here on this diagram. Okay, so it's really just a matter of reading the diagram in another direction, and you can rewrite this correlation function as something which is a difference of traces of powers of your transfer operators intertwined with these operators A tilde and B tilde. Okay, and a really crucial consequence of this for us is that, so if you denote by lambda 1 and lambda 2, the largest and second largest eigenvalues of T, so with multiplicity, so the modulus of lambda 1 is strictly larger than the modulus of lambda 2, then you will have that if you denote by epsilon the ratio between these two eigenvalues, then this correlation function will be upper bounded by some prefactor here that depends on T, and then this ratio epsilon to the power k and the operator norms of your observable, which means that indeed the correlations between these two one side or one column observables are decaying exponentially with the distance separating the two sides or columns at a rate which is simply given by the absolute value of the log of epsilon, or if you want, a correlation length which is 1 over the log of this ratio epsilon. So the smaller epsilon is, the smaller the correlation length. And that's really, if you want, like for a mathematician like me, it's really great because we have completely rephrased this operational problem of trying to understand like what's the amount of correlation as a very neatly posed problem about random matrices, which is like if you're looking at a random transfer operator T that you have obtained from your random MPS or PEPs, what are the typical values of its largest and second largest eigenvalues? And that's what we're going to try and answer now. So let's start with the MPS case. In the MPS case, the results are really nice. I mean, they're actually optimal. And really somehow, yes, you cannot hope to get anything better. So let me try to explain what we obtain. So that's what we do. We try to understand what is the typical spectral gap of this transfer operator, and the result that we get is the following. So we can show that. So when D and Q grow with probability going to 1, exponentially fast, in fact, you have that the largest eigenvalue of T will be going to 1, and while its second largest eigenvalue will be going to 0, and the ratio between the two, if you want to make a quantitative statement, it will be typically upper bounded by something which will be of order 1 over square root D. Okay, so it will be very small when D is large. And of course, so as an immediate corollary of this result, we have a result on the correlation length of our random MPS, and namely that, again, when D and Q grow with probability going to 1, the correlation length of this random MPS will be going to 0 and will be upper bounded by a quantity of order 1 over log D. Okay? So before I give you a very quick idea of how we can prove this result about the spectral gap of this random transfer operator, let me just mention that in fact, I mean, similar results about like typical spectral gap of random transfer operators were obtained before on slightly different models. So instead of looking at a model like ours, where this transfer operator is composed of independent Gaussian matrices, some models were studied where this transfer operator was composed of independent Haar unitaries or was composed of blocks of a bigger Haar unitary. And so these models were studied for slightly different reasons than really like trying to understand correlations in MPS. And namely, they were studied in order to construct a so-called quantum expander. So I don't want to spend time like really talking about this, but just to, in case some people know about this, like to connect with slightly different topics. And in fact, as a side result of this statement here, we have that our Gaussian model for transfer operator provides a new example of a random construction of a good quantum expander. Okay, so now, very, very briefly, to give you just some kind of idea of what's going on in the proof. So let's say that the idea is to try and find a good candidate for an approximate first eigenvector for our random transfer operator T. And indeed, what we would like to show is that in high dimension, this transfer operator T will be with high probability very close to being the projector onto this first eigenvector. And our candidate for this will simply be the maximally entangled state psi in CQ tensor CQ. And then what you do is, okay, so here this transfer operator T is not Hermitian, and it's actually a bit of a problem, but for the sake of simplicity in this presentation, let's just do as if T were Hermitian, and like really forget about like subtleties between the difference between eigenvalues and singular values. So let's just pretend T is Hermitian, and in this case, you have by the minimax principle for singular values that if you look at the inner product between T and this maximally entangled state psi, this will provide a lower bound on the largest eigenvalue of T, while if you look at the operator norm of T times the projector to the complement of this maximally entangled direction, then this will provide you an upper bound on the second largest eigenvalue of T. And then, well, what you have to show is like in the first step that on average, these lower and upper bounds are good. So you can compute the average of this inner product. It's very easy to show that it's actually one. You can try to upper bound the average of this operator norm here. This is a bit more complicated, involves some like Gaussian moment computations, and you can show that it's upper bounded by something that scales as 1 over square root of t. And then in the second step, you would like to show that these two quantities actually have a very small probability of deviating from their average. So it's like this concentration of measure phenomenon. And for this, you need to use some slightly refined version of the standard Gaussian concentration inequalities. But I'm not going to say much more on this. It was just to give you a flavor of what are the tools that are used. Okay, so now let's move on to the PEPS case. So as I said, so in the MPS case, the results are really nice. In the PEPS case, they are definitely not as satisfying, and which is also why afterwards we want to go to this other approach involving the parent Hamiltonian, because the approach to the transfer operator for the PEPS case is not that satisfying. So indeed, what we need to assume for the results to be interesting is that our physical dimension D and bond dimension Q are actually growing polynomially with the number of sites in a column M, like this number M of sites in a column. So, okay, we need to impose actually some more precise scaling for this like polynomial growth. I mean, it's really just an artifact of our proof method. So yeah, it's not so interesting to really study what are the range of powers that we are allowed to take or not. But anyway, so if we're in this regime where we impose that D and Q are growing polynomially with M, then we can show that a bit as before, that with probability going to 1 as M, D, and Q grow, the largest eigenvalue of the transfer operator Tm will be going to 1. Its second largest eigenvalue will be going to 0, and a ratio between the two, which will be of order 1 over M to some power. Okay, and again, as an immediate corollary, we have that with probability going to 1, as all these parameters grow, the correlation length of our PEPs will be going to 0 and upper bounded by something that scales as 1 over log n. So of course, as I've just said, so the main issue in this result is that it's valid only in the regime where D and Q grow polynomially with M. I mean, it's something that that often happens when you're trying to understand things about PEPs. And let's say that one way of really like enforcing the scaling is by doing like what people call a blocking procedure. So it means that you start from a lattice that is a tiny bit bigger, if you want, and then you, before you even start your construction, you redefine one site as being a sublattice composed of log n sites. And so by doing this, what you have redefined as being one site by construction is something where the physical and bond dimension have been blown up, and then you're in the correct regime. Okay, and then again, so here I'm going to be even briefer on trying to explain what's going on in the proof. I mean, it's really much more nasty than the one-dimensional case. So I will just tell you that somehow the main philosophy is to try and do some kind of recursion procedure that uses the MPS result as a building block. But then I mean, because of these dependencies between the operators composing this transfer operator, things are really getting a bit more more complicated to handle. And in this case, what will be our candidate for an approximate first eigenvector will simply be the maximally entangled state tensorized n times. Okay, so I think that's all I wanted to say about like the transfer operator approach. So now I would like to tell you a bit about this second approach that we took, which consists in trying to upper bound the typical correlation length of our random MPS and PEPs by lower bounded the typical spectral gap of their associated parent Hamiltonian. So first of all, let me explain like what is the parent Hamiltonian associated to a tensor network state. So it's, if you want, it's a local Hamiltonian which has the tensor network state as ground state, and it's known that so if you're in what is called like the injectivity regime for your tensor network state, so what this means is that your one-side tensor, when you view it as a map from the bond space to the physical space, is injective. Okay, so I've represented this here by adding some arrows on what are the input and outputs of your tensor. And then, so if you're in this injectivity regime, it's actually known that the tensor network state is the unique ground state of its parent Hamiltonian. Okay, so that's really the regime where we will put ourselves now in order to make statements about the parent Hamiltonian. And so, okay, so why is it interesting to study the parent Hamiltonian of a tensor network state? Well, it's known that if the parent Hamiltonian of a tensor network state is gapped above its ground state energy, then the correlations between two observables on subregions, and in fact, like not necessarily supported on a column or anything, just any two subregions of your network. So the correlation between such observables will decay exponentially with the distance separating the two subregions. And this, I mean, follows from different results. So one way of proving this is by using so-called Lieb-Robinson bounds, and another way is by using so-called detectability lemma. So that's really interesting for us, because it really means that again we have like rephrased this operational problem of trying to understand amount of correlation in a tensor network state by trying to understand, so for a random parent Hamiltonian corresponding to our random MPS or random PEPs, what is the typical spectral gap of between like its smallest and second smallest eigenvalue? Okay, so I mean, I'm not going to describe very precisely to you like how you construct this parent Hamiltonian. I mean, there's a canonical construction that you can do when you are in this injectivity regime. So the only thing I'm going to tell you is what is the injectivity regime in our case. And it's very easy to identify what is this regime, because if you remember our one-side tensors here, they are simply Gaussian maps. So they're going to be almost surely injective as soon as the dimension of the output is larger than the dimension of the input. So for the MPS, it's going to be for d larger than q squared, and for the PEPs, for d larger than q to the 4. So we will put ourselves in this injectivity regime. And in this regime, the parent Hamiltonian H of both our MPS and PEPs is going to be a two-local frustration-free Hamiltonian whose unique ground state is going to be the MPS or the PEPs. So frustration-free means that the global minimizer of the MPS or the PEPs will actually also be a local minimizer. So it will minimize each term in the Hamiltonian, and being two local means that each terms in this Hamiltonian will be acting non-trivially only on two neighboring sides. Good. And now, so let me state the results that we can obtain. So the nice thing is that really the approach is kind of almost identical in the MPS and the PEPs case. So we get results that really somehow behave the same for both cases. And so I'm stating them together in this theorem here. So what we can show, what we have to do is to impose that we are not only in the injectivity regime, but if you want in somehow super injectivity regime. So we have to impose that d is larger than some power of q, which is equal to 4 in the MPS case and to 14 in the PEPs case. So beyond just the injectivity regime, which would be q equals like here the power 2 in the MPS case and a power 4 in the PEPs case. But if we are in this regime, then what we can show is that with probability going to 1, as d and q grow, the spectral gap of the parent Hamiltonian, of this random MPS of PEPs, will be going to 1 with, this error here, which is 1 over some small power of q. And and maybe, again, just to give you an idea of how we can prove this kind of result. So what we show in our proof is that the projectors that compose this parent Hamiltonian H typically almost commute, because if you have almost like if you have a Hamiltonian whose terms commute, it's very easy to understand the spectral gap. So here we show that they are typically almost commuting, and the way we prove this is by constructing, so from the two-side tensors composing our random MPS of PEPs, we construct some operators which we can show are going to be typically very close to the terms commuting composing the Hamiltonian, and themselves almost commuting, which will imply the same for the terms composing our Hamiltonian. And the technical tool that we use here is that a Wishart matrix, which has a large enough parameter, if you rescale it suitably, is going to be very close to the identity. So it's really just some very standard result from random matrix theory that we use as a building block in our argument. And as a corollary of this, we can get a result about typical correlation length. So again, we have to put ourselves in this superinjectivity regime where D is sufficiently large compared to Q. And in this regime, we can show that with probability going to 1, the correlation length of our random MPS of PEPs goes to 0 as 1 over the log of Q. And just one thing I would like to say about this consequence, that if you try to just use a bit naively the detectability lemma, then this will only give you a rough upper bound on this correlation length. And namely, you will be able to show that typically this correlation length is upper bounded by a constant. And if you want to get this stronger result, what you need to use is a refined Lieb-Robinson bound that was proven recently by these people, and which is suited to the case where you know that the terms composing your parent Hamiltonians have a small commutator, and which is precisely something that we are able to prove, because it's what we actually use in our proof for this spectral gap result. Okay, so I'm done with this second approach. In the very few remaining minutes that I have, I would like to just give you some open questions and a few perspectives. So clear open questions at the end of this talk. So about this first approach through transfer operator, the question that remains is could the results in the PEPs case be improved so that imposing that D and Q grow polynomially with M is not needed? And what is clear that with our current proof techniques, probably the exponents could be optimized, because there are several places where we probably lose something, but we wouldn't have any way of really getting rid of this limitation. So in order to do it, you would have to really think of a different approach. And about the parent Hamiltonian approach, the clear open question is can this validity regime, of D being larger than some power of Q, be improved all the way to the injectivity regime? And here I would say that our proofs are likely to be suboptimal, and in fact there is no a priori obstruction why we wouldn't be able to go all the way to this injectivity regime. It would just require much more work, but a priori there is no obstruction. Okay, then a bit more general question. Here what we are doing is that, so we start from a ground state of a local translation invariant Hamiltonian that we construct at random, and then we try to study the spectral properties of this corresponding Hamiltonian. But of course, you could ask the question, what about directly constructing this Hamiltonian at random and trying to study its spectral properties? And this is an approach that's been taken by other people, but there are still a lot of open questions there on what is going on with the spectral gap of this guy. And then last, maybe open question, what about studying other models of random tensor network states? So for instance, you could want to look at a different distribution for the one-side random tensor, so something which is not unitarily invariant, something that has some symmetries, and this would really allow to say something about the typical properties of tensor network state that have a local symmetry, and try to understand what happens with this decay of correlation, etc. And another way you could generalize the results is to try and look at different geometry for your underlying graph, G. So a regular lattice, but in higher dimension, it's likely that some of the results maybe would remain true, even if it would become, of course, much more complicated each time you add a dimension. But then also completely different geometries, like graphs that have a tree shape, like some hyperbolic graphs that appear in the context of ADS-CFT correspondence. This could also be very interesting. So I think I'm actually out of time, so I will just skip this last perspective slide. I mean, I'm very happy to talk about it during some coffee breaks with people that would be interested. And so I will just leave you with the list of references that I mentioned in the talk. And thank you for your attention.
Okay, thank you very much, Cecilia, for a very nice and interesting talk. We do actually have a few minutes for questions. So I want to remind everyone that you can ask questions via the Q&A feature. And I can also try to see if there are questions on YouTube, actually. Maybe while we wait for a minute or so for the questions to come in, can I ask you, you mentioned that your results for the MPS are essentially optimal and that you know that. But for the PEPs, do you have an idea how far they could possibly be improved, or is it really open?
For PEPs, I think everything is basically unknown. I mean, I mean, again, I think, I mean, it seems that somehow, so we know that through the Sprint Hamiltonian approach that you can prove this this decay of correlation even without imposing this polynomial scaling of the physical in one dimension. But it's not completely preventing the fact that in order to show that the transfer operator has a large spectral gap, you actually need this polynomial scaling. So it's, I mean, it would be weird, but somehow we are not able to get rid of this, but probably just because you have to argue in a completely different way, and just trying to reproduce what we are doing in the MPS case and in the two-dimensional cases is just not the right way of doing it. But nothing is known.
Okay, thank you. Okay, we just had a question coming in. So Daniel Stelfranza would like to ask, is the case that the dimension goes to infinity, the states in your model converge to a product state as the correlation length is going to 0?
So in the, I mean, so sorry, for when, which
Sorry.
Dimension going to infinity was he asking? Like the,
in the case
probably I
that
can
the
see
dimension,
it. Let me just,
you can probably see it as well, yeah. But in the case that the dimension goes to infinity, do the model
it's somehow,
converge?
yes, it's somehow what it's saying, because say if we look at the MPS case, like the case where it's really very simple to understand what's going on, what we see is that if you want the correlation length is really upper bounded by something like that depends on the physical dimension d, and when this dimension grows, this quantity goes to 0. So in the end, the bond dimension is here just to guarantee that things happen with high enough probability. But let's say if you're just interested in something happening with probability at least 1/2, you can fix this bond dimension to being above something that you need. And then if you make the physical dimension grow, yes, you will see a correlation length that becomes that goes to 0. But yeah, and the thing is that the result is really valid for any respective scaling of physical in one dimension. So yeah, if both grow, the thing will be true with probability going to 1.
Thank you. Okay, we have like 1 minute left. Let's see if there's a last question coming in or something. You mentioned these extensions that you might want to look at. Do you have any concrete examples or something where the same techniques might apply? Or
Yes, like trying to, I guess so. Trying to look at this in a different context with a different geometry of the graph. I think there it's not really trying to quantify amount of correlation that you. I mean, it's not really the same kind of thing, but maybe different ideas of trying to also understand the amount of entanglement, which I didn't really mention at the end. But this is also something on for MPS or for other kinds of tensor network state, trying to really not quantify correlations with in the end, it's more like like you're looking at classical correlations between the outcomes of your observables, but trying to quantify something that is like intrinsically more quantum, trying to really quantify the amount of genuinely multipartite entanglement inside your tensor network state. And this is really something like whatever the geometry of the underlying graph G that you would like to be able to do it.
Okay, thank you. Let's do one last question. There's one was asked on YouTube by Quantum Danmaku, if I see that right. Is there any relationship between random MPS, as in your definition, with quantum states generated by random circuits, staggered layer style? Do you think any of these results carry over there?
And that's a good question, and it's like indeed something that at least when I'm saying like trying to understand like typical amount of entanglement in like say in any kind of like really physically relevant state. So there's this class of tensor network state, but also things that are like outputs of say like a random quantum circuit, and this is yeah I mean I don't have a clear answer yet, but this is definitely something that I would be interested in understanding, of trying to see if you observe things that are similar in and how things scale, like with the depths of the circuit or things like this. So I mean I don't have an answer, but it's definitely something that I'm looking at.
Okay, thank you very much. I think we have all questions answered, and we are now perfectly on time for the coffee break. So let me thank you again for your very nice talk. And I want to remind everyone that there's now a coffee break, and you can join on Remo, if I see that, and for some socializing. And you can also find the link in the chat. So yeah, hopefully see you there, and please all enjoy the rest of the conference. And yeah, bye.
Thanks. See you there.
See you.
Hello, everyone. Welcome at the first morning session of Monday morning session of TQC. Today we will have five wonderful talks. They will go all super quickly, but if you are interested in these topics, I welcome you to watch the extended talks on YouTube. Our first speaker today will be Dominic Berry, who will tell us something about quantum chemistry algorithms. Dominic, take it from here.
Yep, good. So it is a little bit difficult to get this working, but it's showing the second slide here. So I'll just go from here rather than trying to work out how to get it back to the first slide again. So what we're looking at is how to simulate quantum chemistry with the best possible efficiency. And this slide is describing our general method for doing these types of algorithms, which is using something called qubitization, which is based on a linear combination of unitaries, where you have a Hamiltonian, which is given as a linear combination of HLs, which are unitaries, and you construct a step of a quantum walk where these P operators are preparing a superposition, there we go, and they are with amplitudes which are going like the square roots of the weightings. Then you do a controlled HL and invert this preparation and then do a reflection about 0 on this ancilla qubit. This first line is the ancilla, and this line here is the target system. And the net effect of that is it's like having a operation W, which is a function of the Hamiltonian. And that's useful if we're doing phase estimation, because we can do it directly on this operation W and determine energies of ground states, which is what people are interested in the quantum chemistry. In the case of molecules, we have a general form of the electronic structure Hamiltonian that looks like this, where the important part here is that you have this term with the VPQRS, which has n to the 4 terms in it. And the complexity of these simulations tends to go like the amount of data which is needed to describe the Hamiltonian. And there's also an important feature which is called lambda here, which is essentially a sum of weights in this linear combination of unitaries. So the general goal with these simulations is to reduce lambda at the same time as reducing the amount of data needed to describe the Hamiltonian. So the method we're using is a representation called tensor hypercontraction, where you take this V and describe it as a contraction over these tensors with the chi and zeta. And the important feature here is that the number of parameters is going like order n squared instead of order n to the 4th, which greatly reduces the amount of data needed to represent the Hamiltonian, but it is also increasing the value of lambda. So to reduce the value of lambda as well, we further describe it in this form where you have annihilation and creation operators C, dagger, and C, but these are actually for non-orthogonal orbitals, which would not usually require a non-orthogonal operation to transform the state into this basis. But it turns out that because we're using a linear combination of unitaries, what we can do is transform into these different orbitals separately for each part in the superposition. And that entirely gets around the problem of these things being non-orthogonal. And the net result is that you, at the same time as having a small amount of data, have a small value of lambda, because the lambda is now essentially this sum over absolute values of zeta, instead of being this huge sum like this before. And then the results that we get look like this, where the bottom line is our new results. And the important number here is this 5.3, which is a number of Toffolies, which we're estimating are needed for the estimation of energies for FOMOCO, which is a significant improvement over the complexities for prior work. We also find that when we're looking at scaling to larger systems, we get the best scaling to larger systems where it's about a n squared scaling versus about an n cubed scaling for some important work by Microsoft last year. We also look at methods for reducing the number of ancillas that are needed by looking at how many ancillas are needed in different parts of the algorithm and spotting bottlenecks. And it turns out that this QROM we were using for preparation was a major bottleneck, and we were able to rearrange our algorithm to reduce the maximum number of ancillas needed. And as a result of that, with about a 0.1% error rate in the surface code, we could get away with 4 million qubits and an estimated runtime of less than 4 days, which is a major improvement over prior work. And if you could get down to 0.01% error rate, then you could get away with just 1 million physical qubits. So just the conclusion slide here is that the efficiency is the best yet because we've reduced the effective size of the Hamiltonian in that lambda value, as well as representing the Hamiltonian with a small amount of data. And for the important case of FOMOCO, we have about a factor of 2 improvement over the best prior work, as well as the best scaling to larger systems. And I think that's my 2 minutes up, so I'll let you ask questions.
Thank you, Dominic. Do we have any questions, either in the chat or on Zoom or on YouTube? Mm-hmm. Yeah, maybe I can ask the first question. Dominic, you've been working on improving these techniques for FOMOCO for a few years now. Do you see the estimates do you expect that these estimates will get significantly smaller in the future? Or do you think we are already reaching the limits on the number of qubits one would need?
Well, I think this is tending to reach the limits. We have a new results using quite a different method with plane waves that we had a very long paper out on the archive for last month. And we think we can still do some extra tricks to improve the complexity there, but it's my expectation is probably for the case of FOMOCO, it's still not going to be as good as this, because this is sort of really efficient, but this sort of alternative approach, it might potentially be very good for the possibly larger systems. So we still need to look at, so what's the scaling of the complexity going to be for larger systems? So maybe for sort of FOMOCO's a real starting challenge one that we expect to be able to do on early generations. But if we're then looking at larger quantum computers and larger systems, then maybe we can do better.
Mm-hmm. Okay, thank you.
Mm-hmm.
Okay, do we have any questions? Yeah. Yeah, so here you were specifically talking about FOMOCO, but do you also see these techniques being used for lattice systems?
Oh, well, the case with the plane waves, which we just released last month, is going to be more useful for the lattice systems. So, yeah, so that's the real case where it'll have an advantage. But the plane waves is so efficient that we expect it's going to be also competitive for molecules as well. And we're still looking at doing extra work on applying it to molecules.
Mm-hmm. Okay, thank you, Dominic. So let's give space to our next speaker, Anthony.
Share.
All right. Yeah. So our next speaker will be Anthony Chen, who will tell us about concentration bounds for random product formulas.
So I believe you can all hear me and see the screen. Okay, before I start, I should be very thankful for everyone for being here and hosting the conference. And let me just give a very quick review of what's happening here. Okay, so in this work, we're going to talk about random product formulas. I'm Anthony, and this is joint work with Robert, Richard, and Joel. We're all at Caltech. All right. So we're going to mainly focus on Q-drift. So it is one example of random constructions of product formulas to do a quantum simulation. So before talking about Q-drift, we better start with its very close cousin in the deterministic setting. It's a very simple first order formula. It's called Lee-Trotter formula. Okay, so what it does is just to cycle through all these terms. Okay, and because you have to put all of the terms down to give you this dependence on L, the number of terms in a Hamiltonian in the gate count. So here L is equal to 3. However, in larger systems, in this, I guess, quantum chemistry or in this all-to-all connected system, you're going to have a fairly large number of L. And that's one big problem, at least one bottleneck for these deterministic constructions of product formulas. And today we're going to talk about these random methods called Q-drift, and it's able to remove the dependence on L, number of terms, by using a quantum channel. So all it does is to randomly sample each one of these. And by taking expectation, by applying this quantum channel, it's able to achieve this gate count that's independent of L, the number of terms in the Hamiltonian. So it might seem that randomization is giving us something good. It removes this parameter L. However, to give a fair comparison, we should really compare with the state of the art, the best deterministic Suzuki constructions. In particular, we're going to compare with those with commutator scaling in this recent work. So we immediately see that Q-drift is not going to be great at late times because it has a t-square dependence on time. So that's set. However, because of this dependence on L, the number of terms, when L is very large, there's going to be a time window for which Q-drift has an advantage at early times. So start with these local cases where L is very small, you see that Q-drift is not doing very well. However, if you make L larger and larger, and in one of these systems, this K-local SYK model where we can actually plug in all the numbers, you see that the overhead here for Suzuki formulas is going to be larger than Q-drift. Therefore, there's going to be a time window, an early time window where Q-drift becomes advantageous. So we now established that randomization procedures is able to give you some advantage, even though the advantage is only at early times. It is something that deterministic constructions cannot do. And in this talk, we're going to understand what's behind Q-drift. Where is this speedup coming from? So in the derivation of Q-drift, in this analysis of quantum channel, it's all very clean and elegant. However, it's not entirely clear what's the answer to this question. And in this work, we're going to study each of these instances. Okay, so you're just going to randomly sample a sequence of gate, but you're not going to mix them. You're not going to take the mixture of Q-drift. Okay, so this guy is the mixture, and we're going to ask, how good are these guys? If they're already good, it means that mixing is not really essential for this speed up. But okay, so let's just see what happens here. Okay. So in summary, as the title suggests, random product formulas actually concentrates. So if we look at this deterministic construction, there is this factor of L. And then if you just draw a random gate sequence from Q-drift, so this V is a random sequence of gates, is a unitary, then these already concentrates near the target. Okay, you don't need any mixing. And here is the gate count you require. And you see that you remove the factor of L and replace it by a factor of N, which is a system size, number of qubits. Interestingly, if you only care about fixed input state, then you would ask about the trace norm instead of the spectral norm. And mysteriously, this gives you an automatic speedup. Okay, it further reduce this factor of n and then give you a better gate count. So this is in sharp contrast with deterministic improvement with fixed input state. There you usually need knowledge of the input state. But here, the algorithm know nothing about the input state, okay, as it is unconditional. And somehow this feature is rooted in a high-dimensional probability. So very interesting, we get these two different cases that has different gate count. And finally, let us compare back to the original performance of QDrift. You see that what mixing is doing here by using a common channel is really only giving you a 1/epsilon improvement. So very nice, we now have the entire picture of what QDrift is doing, but I should emphasize that this entire framework works for any random product formulas. And for future work, we could also think about de-randomization instead of randomization, since all these constructions are for existence, okay, so they're not explicit. And also we expect these martingale tools that we use to analyze these results will be useful in many other places. And these different notions, we expect them to show up in totally different contexts. And this is all I want to quickly talk about, and I'll take any questions you have.
Thank you, Anthony. That was a very nice talk. Do we have any questions coming from either Zoom or YouTube? Please type your questions in the chat window. And if there are no questions at the moment, so I personally find it quite surprising that you are getting this much better scaling for the fixed state. Are you making any assumption about the state that is fixed, or is this something about typicality for the state?
Yeah,
could you maybe talk more about why you are getting the speed up, like the better bound?
Yeah. So it's unconditional. It doesn't care which state it is. It could just be any state in the Hilbert space. The point here is that it is okay. So this is in sharp contrast with deterministic setting. So there you really need to know about which state it is to do some analysis and say, hey, this is where the speed up can come from. But here in a randomized setting, this is rooted in high-dimensional probability. So just because we're dealing with vectors, it gives you a speed up over the fluctuation in matrices. So matrices has more fluctuations somehow, and vectors just don't have that many fluctuations. So the bound just get better. So it's unconditional.
Thank you.
And the algorithm also know nothing about the state.
Okay, we still have some time for one or even two questions. So yeah, I don't see any questions coming in. So Anthony, can you then maybe mention something brief about going beyond product formulas?
Oh yeah, so if you're interested in just about the mathematics, I suppose. So here, the tools we're using is called matrix martingales. It's actually fairly modern in these high-dimensional probability communities. And here we're studying random products of unitaries, and it turns out you can make them into martingales. But martingales in themselves are fairly general. For people who are familiar with probability, martingale is just a very broad class. It could be scalar valued, it could be vector values, it could be matrix valued. And there you have all kinds of these very nice tools you can apply for many different contexts. And here we believe that whenever your problem setting has randomness and matrices or random vectors, these large deviation bounds are going to be helpful in those settings, especially in these content information settings. And it would give us these kind of surprising non-intuitive bounds, such as these improvement when you have fixed input state. And for this particular example I'm giving, we're studying operator growth. So it's like a dynamic property of random Hamiltonian. So there you have your Hamiltonian is going to have coefficients that's chosen randomly, and we're able to get concentration results for the behavior.
Okay, so let's thank Anthony again. And now we will have our next speaker, Daniel.
Hi.
And Daniel Stickelfranca will tell us about quantum advantage in linking verification and simulation.
Thanks a lot, Maria. Just one sec. Can you see my screen?
Yes.
Perfect, thanks. So yeah, thanks for the organizer of this conference and for giving me the opportunity to speak here today. So I'm gonna talk about a game of quantum advantage, linking verification and simulation. This is joint work with Raul Garcia Patron. And you find the paper with more details on the archive, or also check out the talk on YouTube. And this is a NISC talk, but we also have some proofs. I should warn you about that. And you see the word verification in the title. I should also say that we do not mean verification in the spirit of Mahadev and other works where we have really a full-scale fault-tolerant quantum computer. Where in this work, we're concerned about verifying the claims we've seen last years of quantum advantage that were often followed by disputes of those claims and then sometimes even rebuttals. And I also made the questionable choice of making this a Game of Thrones theme talk because a colleague of ours mentioned that the title sounds a bit like a Game of Thrones novel. So the whole idea here will be to try to devise some formalism where we have a game between two parties trying to get quantum advantage and try and see what conclusions we can draw from it. So the first guiding question of this work was to formalize this whole process of party A claiming, oh, I have achieved quantum advantage, and party B disputing that claim and saying, actually, with my desktop laptop, I can do essentially as well as you're doing for the task at hand, prove me wrong. And well, we developed a game for that I believe allows us to draw some interesting conclusions about the limitations of the current quantum advantage proposals and the connections between the whole process of verification and classical simulation. And I think that with our game, you can also easily fend off some recent spoofing strategies that were out in the literature, like one by Penn and Zhang, where they claim to have spoofed the recent random quantum circuit sampling experiment by Google. Another important question for this work are, of course, what can we learn from this game besides getting some new strategies for weeding out spoofing strategies. And I think that in a nutshell, what we see is essentially that right now, as we know, that it's very hard to verify quantum advantage claims based on random circuit sampling or boson sampling. Essentially, they seem to take exponential time, and we're already at the limit of what we can do with classical computers. And it is therefore very natural to ask if we can do better than what we have right now. And what we show is that if you could easily distinguish or efficiently distinguish the quantum advantage distributions we're sampling from right now from some easy distributions, so let's say the uniform distribution or some other distributions you could efficiently sample from, then in principle you could approximately simulate quantum advantage experiments. So we make this connection between how easy it is to distinguish a quantum like sampling from a quantum advantage distribution and also from just a very trivial distribution. And we show that if you could distinguish, like giving a very simple distribution in the quantum advantage distribution, you could also simulate this experiment. So it's, unless we change our approaches to quantum advantage, then it might be very hard to verify them efficiently if we also believe that they are hard to also approximately simulate. And maybe let me just quickly tell you how the game works. So the game essentially works by you have the one player who is Littlefinger, who claims he has achieved the quantum advantage, and you have a skeptic, Tyrion, who then disputes this claim and says, well, actually, as far as I can tell, you have a very noisy quantum computer. very low. There's a lot of noise going on. So I'm just going to say you're sampling from the uniform distribution, say. I think that's a good proxy for what your quantum computer is doing. And we then put the burden of disproving this claim on the person making the extraordinary claim, namely that they have reached quantum advantage. And that person needs to provide a function that is able to distinguish the outputs of their distribution from the quantum skeptic. And the quantum skeptic is then allowed to update his guess as to what the quantum computer is doing in light of this new evidence. And if the quantum skeptic can also reproduce the statistics that have been shown so far, then it is again the job of the person claiming quantum advantage to provide new functions that are able to distinguish whatever this classical skeptic is doing from this quantum advantage distribution. And with this very basic framework, we are then able to draw our conclusions by choosing different strategies for different problems. And with that, I think I'm done with this very brief summary and would love to take some questions from the audience.
All right, thank you, Daniel. Do we have more questions? Okay, so do you have any expert opinion about how would dragons affect the decoherence in the supremacy circuits or quantum advantage?
That's a very important question. Where I think that's we're gonna do that in some follow-up work. It seems to be a hot topic at the moment. Yes.
Also, you were specifically talking about the uniform distribution. What are some other distributions that one could now successfully suggest for spoofing?
Yeah, so the uniform distribution, it plays a significant role in this work because, like if you could easily or efficiently distinguish from the uniform distribution, then you could also, what we show is you could easily spoof the current measures used in the experiments, like heavy output generation or so on. So that's why the uniform distribution has an important role, because if you could even distinguish from that one, you could spoof the current proposals. So other distributions you could aim for, I guess, are like the one by Penn and Zhang, where you just you hard code some qubits to be 0 and then try to find heavy high probability outcomes in the subspace where a certain number of bit strings is set or is constant. So that's another distribution that is interesting to look at. Oh, I see there are also some other questions from the audience.
Okay. Yeah, so we have a question from another panelist.
Sure, I can ask the question. So you were saying that the ability to distinguish hard quantum distributions from easy classical one implies being able to approximately simulate the sampling task, or at least the quantum distribution. And I was wondering, how is this compatible with the existence of Mahadev's verification protocol? Because in principle, I could use this to do the distinguishing between these distributions classically, no?
Mm-hmm. Well,
oh, sorry, yeah.
No, sorry, it's just because we're not talking about general distributions, right? We are talking about essentially these random quantum circuits, for instance, because they have this, the property we actually need is that these are very high entropy distributions. So they are, their entropy is essentially maximal. And when you are in this setting where you're sampling from an output distribution that is essentially has maximal entropy, then these two ideas of distinguishing and approximately sampling are the same. But this doesn't apply to arbitrary
I see.
distribution.
So does it rule out also verification, like interactive verification protocol? Because I guess this is the key in like Mahadev's protocol, that there is a back and forth construction that allows.
No, I don't think so. No.
Okay.
As far as I know.
Thank you.
All right, so we have more questions in the chat, but hopefully Daniel will have time to answer these questions during the coffee break after. So at the moment, let's thank Daniel again, and let's get ready for our next talk. And our next speaker will be Michal Osmaniek. I hope I'm pronouncing your name correctly. And Michal will tell us more about fermion sampling.
Yeah. Right, is that correct? Yeah. Can you see my slides?
Yes, all good.
Cool. Welcome, everybody. It's my great pleasure to be able to advertise my work here. So I'll be talking about this new scheme for quantum advantage we have. So it's based on passive fermionic linear optical circuits and magic input states. It's a joint project together with Nina Dangia, Mauro Morales, and Zoltan Zimborash. You can go and check our paper on arXiv. Right. I was told that I have 5 minutes, so I'll be very brief. So here is our scheme in a nutshell. We have this circuit, let's say fermionic circuit, that we initialize in tensor product of so-called magic fermion input states. So when you map your fermions into qubits, you can prepare those states efficiently. Those are just the JZ states. Then we apply to the whole system a sequence of either passive or active fermionic linear optical unitaries. So those linear optical unitaries, there are some natural gates that operate in fermionic systems. So passive ones transfer fermion creation operators like that. Active transform Majorana fermion operators in a similar fashion. And then we measure the computational basis, and as in all quantum advantage proposals, we sample from the optical probability distribution. Yeah, this is our proposal in the nutshell. Here are the results that we have. So we prove anti-concentration of output probability distribution of output probabilities in the scheme. Also, we prove average case Shapley hardness of those guys, and we show that it's possible to efficiently certify an unknown fermionic linear optical transformation. Right. So the first 2 results, there are strong evidence for hardness of sampling along the lines that you have, similar to the ones you have for random circuit sampling or boson sampling, for example. Just a comment about how to implement our proposal. So far, we are not aware of like an actual physical system that would be implementing those transformations. It would be cool to have one. But when you map fermions into qubits via Jordan-Wigner transformation, you can realize those classes of gates via circuit of a linear depth in the one-dimensional architecture, and importantly, gates that are required to implement the FLO gates. They are native for superconducting architectures, and they were already used in some proof of principal experiments with quantum chemistry, VQE. Right. So I dare to say it's not hopeless to implement our scheme in practice. Now, our first result concerns that it's possible to do efficient tomography of an unknown FLO circuit. So we have the scheme. I won't be presenting it in detail, but in a nutshell, we can use the structure of FLO circuits to efficiently, to estimate an unknown FLO circuit, like efficiently in the like size of the system, and the quality we measure in the 911. So it's much better than what you would have if you are doing standard tomography. Okay, this is just result on certification. We prove anti-concentration for those circuits. So very briefly, we show that it's yes, it's like with significant probability over the choice of random circuits. Output probabilities in our scheme, they take values that are not too small compared to the dimension, inverse of the dimension of the space. So it's some useful property that you want to have from quantum advantage proposals. And to prove this, we use Paley-Zygmunt inequality and tools from representation theory of low dimensional Lie groups that underline fermionic passive, like fermionic linear optical circuits. And it's important because those guys, they don't form like designs, like as random quantum circuits. They are quite structured. Right. That's all I have to say. Like in about this in this short presentation. Like our last result concerns average case hardness. So what we do, we construct low degree rational interpolation between worst case FLO circuit and generic circuit, and we then use techniques of polynomial interpolation to recover the value of the worst case probability from values for generic circuits. And technically what we do, we use Cayley path deformation that was introduced in in the paper by Movasak 2 years ago. Like the difference, what we do compared to him is that we do deformation level of the full symmetry group that underlines the class of circuits we are interested in, while he was doing deformation level of individual gates in random quantum circuits. Okay, so that's it. I have to say in 5 minutes or a bit more. We propose the scheme for like fermionic analog of boson sampling. So we initialize fermionic system in magic states. We apply random FLO circuits, either passive or active. It's not hopeless to experimentally realize it. We gave, I think, quite strong, let's say, indications of hardness of approximate sampling from the scheme. And lastly, we showed that it's possible to efficiently certify an unknown fermionic linear optical unitary. So I encourage you to check our paper or check the recording of the longer version of my talk on YouTube. Thank you for your attention, and I'm happy to take questions.
Thank you very much, Michał. Do we have any questions?
So I do have a question. Michał, you mentioned average case hardness. Is it hardness of exact sampling or approximate sampling?
No. It's actually hardness. Yeah, I was in this. Like it's average case hardness of approximately computing output probabilities.
Okay.
Yes. Yeah. Of approximately computing these.
I see. And so is there kind of a natural conjecture, I don't know, about some mathematical object like in the other sub-universal proposals where that allows you to kind of extend this?
So
the sampling
probability, you can go two ways about it. So one way is that like those magic, the reason why those states are called magic is that you can use them to perform actual full-fledged quantum computation when you have at least active FLO circuits. So then it's like as in usual, let's say random circuit sampling. But for passive, it's possible to relate scattering amplitudes to so-called mixed discriminants that are roughly speaking superpositions of like sums of determinants, and they were showed. Yeah, so those are the objects you.
Okay.
Like, yeah.
Thanks.
All right. Since we don't have any more questions, we can welcome our next speaker, who will be Ulysses Chabot. I'm probably mispronouncing your name, and I'm very sorry for that.
No worries.
Who will, for a change, talk about boson sampling.
Sure. So let me share my screen, and then this.
Looks good.
Okay. I just have to remove this. Okay. Thank you for the introduction and the occasion to present my talk at TQC. So this is a joint work with Frédéric Grossan, Elam Kashifi, and Damien Markham in Sorbonne University in Paris. And I'm now a postdoc in Caltech. So the name is Chabot. It's a French weird name. And so the talk of today will be about efficient verification of boson sampling. You heard a few minutes before Daniel talking about kind of the importance of like proper verification of quantum speedup. So this is what the talk will be about, or at least one step in this direction. So quantum speedup is like has many different names and definitions, but let's say informally that it is when a quantum computer performs efficiently a task which is like provably intractable for classical computers. And so the kind of natural example about this is factoring, where we do believe that factoring is hard for classical computers, and we have Shor's algorithm that makes it efficient in theory for quantum computers. And that would be like the perfect task to show that quantum computers outperform their classical counterparts, but it turns out that the quantum circuit required to do so at large scales is very hard to build. So instead, people have been introducing, like now more than 10 years ago, sub-universal models that are maybe less powerful than a like fully fledged universal quantum computer, but at the same time probably way easier to build. So one famous example of this is boson sampling. This is the kind of linear optical instance of boson sampling, where you input single photons in vacuum states and into some random interferometer, and at the end you measure the photon number detection. And it turns out that this device, up to some conjectures, does something which is hard for classical computers, which is sampling from the output probability distribution of this circuit. And so now say one comes and build a random quantum circuit or a boson sampling device like in the recent month. How do you verify that the very noisy circuit is doing the right thing? How do you verify these claims of quantum speedup? So the first problem is that it's actually the nature of the computational task at hand, which is sampling. So what this black box does, you can think of this as being the quantum speedup experiment of your choice, and it outputs some like random numbers, and you're asked to verify whether these random numbers are sampled from the right output probability distribution, and there are various no-goes for doing so like directly efficiently. If you just get the sample and you're asked, test that this is the right coming from the right probability distribution, you cannot do it because of anti-concentration. And so instead, people have introduced other methods that are either like partial or assume something about what's going in that box, or are not yet practical. They need a universal quantum computer with full tolerance. And so the setting we're considering in our work is saying, well, we don't have yet like the fully ideal classical verification of these devices. So instead, we may try to give just a bit of power to the verifier. So the setting, you can really think of this as some cryptographic setting where this is your quantum speedup experiment. You don't want to assume anything about what's happening in the box. You request some quantum state, and you're just trusting very simple single subsystems measurement. So you trust this part and you want to verify this state. And it turns out that guarantees on these states can then give you guarantees on the output probability distribution when you perform the right measurement on the state. So the results we got there, you saw the title of the talk. It's an efficient protocol for verifying the output states of any boson sampling experiments with input single photons. And the measurements we're trusting are the so-called Gaussian measurements. These are continuous variable measurements that are routinely implemented in optical labs. So it's called heterodyne detection. It's essentially, if you know what homodyne detection is essentially two homodyne detection kind of bunch together. So here is what the protocol looks like. So you're essentially just running your Boson sampling experiment many times. Each time you get an output state. So here I've represented the same state for simplicity, but you don't need to assume that these states are identical, or they could even be entangled over like all the runs of your experiment. And then what the verifier has to do is in blue here, just measure all subsystems with this heterodyne detection. The output here, alpha, is some complex number, and you do that many, many times, which is efficient in the number of modes of or the size of your Boson sampling experiment. And there's a efficient, again, classical post-processing that goes on after that, which gives you your guarantee on how close this state is to the ideal state. Okay, so I think I'll just conclude here. And of course, if you're interested, you can see the paper, the extended talk. But in a nutshell, the results are this efficient protocol for the verification of photonic quantum speedup. Using only trusted measurement, we make no assumption whatsoever about what's going in the box in the experiment. And it has other applications for certifying multimode quantum continuous variable quantum states. You don't even need to assume that the state lies in some finite dimensional Hilbert space. And the natural question, of course, is there a way to turn this into a classical verification? So this is a work that we have in progress, but yeah, maybe more on this in a few months. So I'll thank you for your attention.
Thank you very much, Julius. Do we have any questions? Until there are more questions come through the chat, could you elaborate a little bit about the measurements?
Sure. So let me maybe just, I do have a slide somewhere. Yeah. So this is the measurement. This oval here is heterodyne detection. So what it does, it measures the quadrature of the electromagnetic field. So it's essentially just this, like you see this dotted red line here. It's a beam splitter. You have the light coming in from here, and then you mix it with some laser light. You measure the intensity here and there. You compute the difference of the intensities, and this is your quadrature measurements. And then if you assemble two of these, so this is a so-called Gaussian measurement because it projects on two Gaussian states, which are kind of the simplest state that you can think of, the continuous variable equivalent of Clifford states. And if you assemble two of these with the right change of phases between the two arms, then what you get is an output composed of two real numbers. You assemble them in post-processing to give a complex number, and this is what you're required to do. What's interesting, actually, it's the same setup that you would use to perform original tomography, but the difference is it's efficient.
Thank you. Do we have any more questions? All right, and yeah, there are also no questions coming from the YouTube either. So in that case, I would like to thank one more time to all the speakers.
Thank you.
And right now we will have a coffee break. Coffee breaks are all in a platform remo.co. A link for it you can find on the TQC's website. And I would like to encourage everyone, especially the panelists, to stop by there for a few minutes and maybe answer more in-depth questions. And so let's see you all in there. Thank you very much, everyone.
Hi, Mark. Can you hear me?
Yes, I'm online. Hello? Hello, hello? Can you hear me? Hello? Can you hear me?
Hi, Mark. Can you hear me?
Yes, can you hear me? Yes, and you?
Yes,
Hello?
yes, yes, yes.
Okay.
Are you ready with your?
Yes. Yes, I am.
Okay. Hi, welcome all. So our session. Welcome to the current session. The first talk is given by Mark Oliver Renaud on covariance decomposition as a universal limit on correlations in networks. So Mark, we have 10 minutes, including questions. So please try to keep the the talk according to the time. Okay, thank you. Over to you.
Okay. So yes. So today I will talk briefly about a joint work I did with Salman Beji, which is about a constraint which can be found over all probability distribution which can be obtained in such a network, whatever the physical model. So I consider a network like this in which I have parties measuring some sources and obtaining some output. They obtain some probability distribution, and I want to see what is the constraint over the probability distribution depending on the structure of the network. And I will do this for any possible physical model beyond classical and quantum physics. So I guess it is quite clear for everyone what is a standard Bell non-locality in which you have several parties. So here 3 in a GHZ scenario, but I could talk about the CHSH scenario. So sharing a source, which they measure according to some inputs, obtaining some outputs. There is a no signaling hypothesis, and they obtain a correlation. And depending on the nature of the source, which can be local or classical, they can obtain some different probability distribution. And there is a set of probability distribution they can obtain. And then I can look at quantum sources and quantum measurements. And with the Bell inequalities, we know that there are some probability distribution which are quantum and which cannot be expressed by any local model. And this was generalized to post-quantum models in which I can obtain even more probability distribution. So people imagine, for instance, the Pierre box which is an hypothetical physical theory beyond quantum mechanics, in which I can obtain even more probability distribution, still satisfying this no signaling assumption. So today, what I want to talk about is different. I want to talk about probability distribution, which can be obtained in networks. So for instance, in a triangle structure like this, in which I have 3 independent sources. So again, in this triangle structure, I can imagine classical model, local models, and I will find a set of probability distribution. And I can generalize these to quantum models or to no signaling boxes. But we see this structure of those sets. And actually, what I want to talk about is not specific model, but all the imagined as of quantum mechanics in these networks. So first, I will tell you what we have in those networks. So I will assume to any potential generalization of quantum mechanics in such a triangle structure, I will assume that it satisfies 2 principles, which are device replication and causality. So what do I mean by those 2 principles? So device replication, it is just to say that imagine that I have some post-quantum theory experiment with 3 post-gamma and 3 post-quantum measurement boxes A, B, C, which obtain some probability distribution. I assume that my theory will satisfy device replication, which means that I am able to copy this device R alpha in order to create a replication of it, R alpha prime, which has exactly the same behavior, but which is independent. And then I assume that I'm able to reorder all those copy devices in a new setup in which I must obtain some probability distribution, Q, which satisfies causality. And causality gives me a couple of constraints. So for instance, the marginal probability of A in this device of Q should be the same as A in that device of P, because A here and A there see exactly the marginal probability distribution of a B and B prime should factorize because B and B prime have no common source. They are causally disconnected. So somehow, what I say is that all imaginable physical model in the triangle obtain probability P, which should satisfy some constraints which are given by the existence of a Q, satisfying a collection of constraints like this in all potential inflated scenario of the triangle. So this is the definition of all potential generalization of quantum mechanics for probability distribution in those network structure. And now we have proven that those correlations satisfy a constraint which is non-trivial, which is this covariance decomposition. So this covariance decomposition was already known for local and quantum models. If you take the covariance matrix of the output of the parties in a triangle structure like this with classical or quantum strategy, it should satisfy some constraint which is given by a sum over all the sources, which depends on the structure of the network. So this generalizes to all networks. And we have proven it. We have generalized it to all imaginable physical model using device replication and causality. So our proof is not completely general, so it does not work for networks in which 2 parties are connected by 2 different sources. It works for local and quantum models. So this is, I think, just a limitation of our proof. And we conjecture that actually it should also still hold this decomposition in this case. We have important and I think interesting technical details in our proof. about a duality or formulation of this decomposition, which requires infinite asymptotic inflations, and generates the notion of embezzlement. And let me conclude very quickly by saying that this is the first universal limit on correlations in general networks for all models beyond quantum mechanics. And yeah, technically we have those important lemmas which generalize, we use a notion of embezzlement beyond available in our proof. So with this, I have time for 2 questions or 3 questions, I think.
I do not see any questions in the Q&A section as yet. So if there are any questions, you can either mention it in the Q&A section, or if you want to ask yourself, please raise your hand and I unmute yourself and ask. Okay, since there are no questions, maybe I request you. So we thank Mark for a nice talk, and then we request you to stop sharing your screen so that the next speaker can do that. Thank you.
Hi, I believe I'm the next speaker. Ah, no, I'm not the next speaker. I'm really sorry. Or am I? What time is it? Yeah, it is. Yeah, okay, good. Sorry about that. Let me share my screen.
Yeah, right.
I want to share. No. I want to share this one. Can you all hear me and see me?
Yes, we can hear you and see you. Yes.
Excellent. Very good.
Okay, so our next speaker is Patricia, and she's going to talk about genuine multipartite non-locality is intrinsic to pure state quantum networks. Patricia, we have 10 minutes for the talk and questions, and I will give you a reminder 2 minutes from the end of the 10 minutes. Okay.
Excellent.
All right, so over to you. Over to you.
Thank you very much. Well, thank you all for being here and listening, and thanks to the organizers for putting on this conference and allowing me to speak. So as the host said, I'm going to talk about genuine multipartite non-locality, which is intrinsic to pure state quantum networks. And this is based on a paper that we published in Physical Review Letters earlier this year, which is joined with Carlos Palazuelos and Julia de Vicente. And then we extended some of the ideas of the paper to mixed states in this archive paper earlier this year as well. Okay, so I'm going to summarize the talk that was on YouTube. I'm just going to throw at you the results just to get everyone on the same page before the questions. So the first thing we did is consider networks like this one over here, where parties share only bipartite entanglement, so they share pure bipartite entangled states, and any party might be connected like this to one or more of the others, as you can see, right? So the theorem says that any connected network of bipartite pure entangled states is genuine multipartite non-local. If you don't know what genuine multipartite non-locality is, the main idea is that it correlates all of the parties in the network and not just a subset, and also not just convex combinations of subsets. And so the power of this result is that it's independent of the topology of the network. So it doesn't matter how these arrows are put somehow, so that I could have an extra connection between, say, these two parties, or I could remove this arrow and put it here instead. It really doesn't matter what the topology of the network is, as long, of course, as it is connected. And it's also independent of the amount of entanglement shared. So as long as these states are entangled, they might be infinitely little entanglement contained in the states, but still the result holds. And this we prove by combining the bipartite inequalities that detect each of the states in the network to make an inequality that detects the genuine multipartite non-locality and then proving that any such network violates it. And we extend this result to deduce a consequence of it, which is that any genuine multipartite entangled state is such that n-1 copies of it, where n is the number of parties in the state, is genuine multipartite non-local. And we prove this by basically building a network of the kind before from the copies of the state. So n-2 of the parties measure, leaving 2 parties entangled. And so we do that once for each copy of the state, and leaving Alice entangled with each one of the other parties. And that's how we deduce that finitely many copies of a genuine multipartite entangled state gives rise to genuine multipartite non-locality. And then we say, that's great. Pure states have this deep property somehow of quantum networks that is genuine multipartite non-local. This is great. This can be useful. Well, it can be useful if you consider mixed states as well, right? Because pure states are very nice and well-behaved, but in an experiment or in a real-life application, you're going to need mixed states. So what about them? Well, the first thing that we can say is that, yes, we are going to have some amount of robustness in a result, but we can't, in general, guarantee even genuine multipartite entanglement in mixed state networks. So again, genuine multipartite entanglement is the entanglement contained in all of the parties together, not just in a subset, and not just in convex combinations of subsets. And so the first thing we study is genuine multipartite entanglement in mixed state networks. And so we have 3 main results. There's more in the archive, but I'll present these 3. First, we have examples of pair-entangled networks that, even though they are pair-entangled, as the name suggests, even though the states individually, the bipartite states, are entangled, the whole network is biseparable, so it's not genuine multipartite entangled. This didn't happen in the pure state case. Then we consider tree graphs, which are the connected graphs, but with the fewest edges. So they don't contain any cycles. Those become biseparable as soon as the number of parties gets large enough. And we also have that completely connected graphs, so those where any pair of parties shares an edge, shares a bipartite entangled states. Those are always genuine multipartite entangled as long as the visibility is good enough. What's the visibility? It's this parameter p, because we consider isotropic states. Turns out that this has like wider applications, but let's worry only about isotropic states for now. And it's a weight p times the maximally entangled state, and the rest of the weight goes to the identity, white noise. So the visibility is basically how good my state is. And so we have, for example, that in tripartite networks, if I have the simplest kind of network where Alice is connected to Bob and to Charlie, but Bob and Charlie don't share an edge, this is biseparable for p below a certain threshold and genuine multipartite entangled for p above a certain threshold. But the interesting thing isn't these particular numbers, but the fact that they are much lower if I have a triangle network. So if Bob and Charlie do share an edge, suddenly I can achieve genuine multipartite entanglement with a much lower visibility. So this is kind of nice. We see a dependence in the topology, and it turns out that this dependence is extreme, because if I go to large networks where I don't restrict the number of parties, in fact, I let it go as high as I want, it turns out that all 3 networks become biseparable. That's not genuine multipartite entangled. For all p less than 1, so for all visibility, that means that has like any amount of noise, basically. As the number of parties grows, so all bets are off. If you want to build a quantum network in the form of a tree, you're never going to have genuine multipartite entanglement. And at the other end of the spectrum, a completely connected network is always genuine multipartite entangled as long as the visibility is above a certain threshold and for all number of parties. And by the way, this threshold is like 0.8 or something as far as we calculate it. So it's not a crazy good visibility that you need. Okay, so the open questions that arise are, well, first of all, what is the network with lowest connectivity that displays genuine multipartite entanglement? So what's in the middle of these two? How many of these edges can I remove in order to still get genuine multipartite entanglement? And also, is this result also valid for genuine multipartite non-locality? How can I get genuine multipartite non-locality from a mixed state network? And finally, this work uses the genuine multipartite framework, which is more connected with the LOCC framework. But could we use, could we come up with some different definitions? For example, one of genuine network non-locality, there are people working on this right now, that may detect genuine network entanglement, where genuine network stuff means whatever you can't create, you couldn't have created in a network. So yeah, our results basically show that the genuine multipartite definitions are nothing to do with the others because you can't use one to detect the other. But is there a better definition that we might use to detect these things? And that's me. Thank you very much.
Okay, I do not see any questions on the Q&A. Yeah.
Can I ask directly? I have a question. So
yes,
it
please,
is about
please
what you just said and what you just discussed about this notion of network or not. So in your definition of genuine multipartite non-locality, what I find not natural is that you can find something which is genuine multipartite non-local of size 3, for instance, using only bipartite resources. So this is what we clearly see in your network.
That's exactly what we exploit,
result,
yeah.
Right? So if you have Alice and Bob violating CHSH and Bob and Charlie violating CHSH, they are using bipartite resources, but according to your definition, they have something which is genuinely multipartite three-way, right?
Yeah.
So is it not a hint that this definition is not the good definition for our intuition of what should be genuine multipartite non-local?
So it kind of depends on what you want to do with the definition, right? These things about like natural or not natural is a bit slippery to me. It turns out that a lot of the applications of multipartite non-locality rely on genuine multipartite non-locality. So you need this to make whatever cryptography, whatever sending messages, whatever you want to do, right?
Sorry, Patricia.
Yeah.
I would request you to take this answering with Mark offline because we yeah, already done with time. Sorry
sure,
about that.
I'll reply on the chat right now and we can.
Yes. Thank you very much. We thank Patricia for the nice talk. And please unshare your screen. Yes, thank you. Oh, and then now the next speaker, Peter.
Yeah, that would be me, I guess.
Great. Yes, so we have 10 minutes and I'll just ping you once when 2 minutes are left, okay?
All right. Okay, let me. Can you see my screen?
Yes, we can see it.
Okay, very good. So I'm Peter Rana from Budapest, and my talk is about a family of multipartite entanglement measures. So let me start with a few words on the background. So this will be
Peter, there is a part of your screen which is black. I think that's some chat or some window of Zoom, I think.
Zoom window, okay.
You minimize it or something. Yeah, this is good. This is fine. Yes.
I don't know. So
yeah, it's good. Thanks. Yeah.
Okay, so first of all, let's define delta k to be the set of all functions and vectors and k-parted Hilbert spaces. So you can think of these as state vectors, but I also want to include those with norm different from 1 for reasons to become clear shortly. These are real valued or non-negative real valued functions that satisfy these kinds of axioms. So they must be locally interinvariant, and for a certain parameter alpha, they must satisfy the scaling property. So this is where the norm of the vector enters. So given alpha, the vector itself is defined on, it's determined by its values on unit vectors. but it must have a certain scaling property, multiplicative under the tensor product, additive under the direct sum, which is maybe a less familiar operation on these vectors, but you can think of it as a superposition of locally orthogonal vectors. So the way you imagine it is that because of this local unitary invariance, you can just change one of the terms to be locally orthogonal to the other one and then take the superposition or just add the two vectors. They're normalized and separable vectors and satisfy this type of inequality for any local orthogonal projections. And so these are the set of axioms that we wish to satisfy by these functions, and this is basically the problem statement is that we're looking for all the functions that satisfy these. So the problem is to classify them. And why are we interested in them? Because of our earlier work that shows that these functions collectively characterize the so-called converse error exponents in asymptotic probabilistic exact LHC transformations. So in a nutshell, that means we take, say, n copies of our initial state psi, and we want to get n copies of our target state phi with the help of LHC transformations. Exact means that we want to arrive at the state exactly. Probabilistic means that the transformation may not succeed with probability 1, but with some slightly lower probability or maybe substantially lower probability. We're interested in the asymptotic setting when n goes to infinity, so the number of copies of the initial and target state goes to infinity. And finally, the converse error exponent refers to the fact that for certain pairs of states, you cannot do this with a high success probability, but it will necessarily decay exponentially. And what we're interested in is the rate of this exponential decay. And I should also mention that if we only look at the alpha equals 1, so there was this sort of parameter alpha, only the alpha equals 1 functions, then this last condition must be understood in the limit sense, then they also characterize things like the asymptotic complexity of matrix multiplication, or more generally, asymptotic rank and subrank of tensors. So here's what is known about the three-party case, where I'm interested in any number of parties, but here's a drawing of the three-party case because it's easier to draw. So there are some kind of obvious functions in this set, namely the norm squared of this vector, and there are also some forms of the exponentiated marginal Rényi entropies. So for each of the three marginals, one can compute Rényi entropies of orders between 0 and 1, and take the exponential and get functions like this. And there are also much less obvious ones, which is this facet of this tetrahedron. From our earlier work, they will have alpha equals 1. And the ones that I'm presenting in this talk is the solid tetrahedron, which is colored with this green color. And this irregular shape says that basically that there might be many more functions that we're not aware of in this state, in this set. So with this, I get to the main results of my work. So one ingredient in this construction of these new elements of this set delta is the so-called rate function or light deviation rate function of simultaneous empirical Young diagram measurement. So what that means is that we think of this psi as a k-parted state, take n copies of it, and decompose each of the local Hilbert spaces. So we have n copies of each of the local Hilbert spaces now according to the Schur-Weil duality, and these are the Schur-Weil projectors, so the projections into the isotypic components of with respect to the symmetric and the unitary groups. So the behavior of these of the norms of these projections is exponential in n, and the rate function is what encodes this exponential decay. So this kind of function that is defined with the help of this tape psi and is defined on normalized partitions. So you can also think of these as probability distributions that are ordered non-increasingly. And with the help of these functions, we define a quantity that's defined as an optimization. I want to take the maximum or the supremum of a certain convex combination of the entropies of this distribution with a penalty term determined by this rate function. And the main result is that if we exponentiate these functions, then we get an element of this spectrum. Yep, so one of the corollaries of these axioms is that if we take the unexponentiated one, so the logarithm of this one, then that would be an additive entanglement monotone. So thanks for your attention.
Okay, thanks, Peter, for the talk. Any questions? Okay, there does not appear to be any questions. So thanks again, Peter. All right, so if you can please, yeah, great. All right, next speaker we have Sarah. Yes, great.
Can you see my screen now?
Yes, yes, I can do that. Yes.
Okay, perfect. Hello, everyone. My name is Sarah Jansen, and I'm a master's student at the University of Amsterdam. And I would like to start by thanking the organizers.
Yes, Sarah. I mean, can you just wait 1 minute before starting your talk? Yes.
A bit too enthusiastic, maybe.
Thank you, thank you, thank you. All right, okay, thanks, Sarah. So our next speaker is Sarah, and she'll be talking on enumerating all bilocal Clifford distillation protocols through symmetry reductions. Please, over to you.
Hey. Hello, everyone. My name is Sarah Jansen, and I'm a master's student at the University of Amsterdam. And I would like to start by thanking the organizers very much for organizing this conference and for giving me the opportunity to talk about our paper, enumerating all bilocal Clifford distillation protocols through symmetry reduction. You can find it here on the archive. This paper is joint work with Kenneth Goodenough, Sebastiaan de Boon, Dion Gijswijk, and David Elkus. As you probably all know, entanglement is essential for many tasks in quantum communication. However, due to experimental limitations, in practice this entanglement is always noisy, meaning that it has a non-unit fidelity with a maximally entangled target state. To increase this fidelity, we can use entanglement distillation. The idea of entanglement distillation is that we start with a number of states with a lower fidelity, and then using local operations and classical communication only, we transform this into a smaller number of states with a higher fidelity. Our goal is to find good performing distillation protocols that satisfy some modest constraints. In particular, we are looking for protocols that only use a small number of states in the input and that only require a single round of classical communication between the two parties. We present a systematic procedure to find such protocols. To this end, we narrow down our investigation from the big space of all entanglement distillation protocols to a smaller but practically relevant subset of protocols and states. Let me elaborate on that a bit more. We consider a system that consists of two parties, Alice and Bob, who share a tensor product of n Bell-diagonal states. These Bell-diagonal states correspond to Pauli noise, which naturally arises in experimental setups. Now, suppose that we have such an initial state. Then we can describe it as follows. Because of the time, I won't go into the details of this formula, but what is most important to remember for now is that we can describe our input state by a set of probabilities. The first step in the protocol now is that Alice and Bob perform a so-called bilocal Clifford operation. This means that if Alice performs a certain Clifford operation, then Bob performs the entry-wise conjugate of this operation. The result of such an operation is a permutation of these probabilities. Next, Alice and Bob measure all but one of their qubits in the computational basis. They communicate their outcomes via classical communication and check for pairwise correlation. If the outcomes are pairwise equal, then they call the protocol successful and they keep the state that was not measured. If the outcomes are not pairwise equal, so like this for instance, the protocol was unsuccessful and they discard all states. In the video, I explain how we can find the probability of success of such a protocol and how we can determine the fidelity of the output state. Now, it turns out that there are some bilocal Clifford operations that do not change the fidelity and success probability. We define the distillation subgroup to be the subgroup of bilocal Clifford operations that contains precisely these elements. We can add or remove an element from this subgroup at the end of our protocol, and that won't change the fidelity and success probability. Moreover, if our input state has some sort of symmetry, so if some of the probabilities that describe it are equal, then there are also operations that we can perform at the beginning of our protocol that won't change the fidelity and success probability. We denote this group of operations by G. We now see that two bilocal Clifford operations, C1 and C2, give the same fidelity and success probability if and only if C2 is equal to first performing C double prime, then C1, and then C prime, where C prime is in our distillation subgroup and C double prime is in this symmetry subgroup. As a result, we can divide our big space of bilocal Clifford operations into smaller sets where all elements in the same set give the same fidelity and success probability. When we are looking for the best performing protocols, it is now sufficient to only check one element from each set. Using this insight, we were able to find all bilocal Clifford distillation protocols up to NS5 arbitrary Bell diagonal states in the input. For the special case of an n-fold tensor product of a Werner state, we found all protocols up to NS8. Among these protocols, we found some protocols that improve upon previously known protocols. In this figure, you can see the increase in fidelity between the input states and the output. The dotted lines correspond to the Dames protocol and generalizations thereof, and the solid lines correspond to the protocols that we found with our optimization that achieve the highest fidelity. As you can see, for NS2 and NS3, the results are equal, but after that, our protocols perform better than the Dames protocols. Moreover, the circuits that we found that corresponds to these results have a comparable depth and number of 2-qubit gates as previously known protocols, which indicates that they are experimentally feasible. Now, of course, this picture shows just one figure of merit, but in our paper, we've included a more in-depth comparison between previously known protocols and the protocols that we find with our optimization. And we have found protocols that strongly improve upon previously known protocols. And with that, I would like to conclude this presentation and thank you all very much for your attention. Are there any questions?
So you are not alone. But I'm sorry, I don't have questions.
Okay.
Okay, thanks, Sarah, for the nice talk. Any questions? Okay, in case there are no questions, maybe Sarah, maybe the next speaker can set up their sharing and so on. Okay, thanks a lot, Sarah.
Hi. Can you see my slides?
Yes, we can see that. So we have 10 minutes, Sarah, and then including questions. So maybe when it's 8 minutes, I'll just ping you. Okay.
Yeah, great. Thank you.
Yeah, still 1 minute to start.
Yeah.
Can I address you as Haley?
Yes. Yes, please.
Okay, thank you. All right, so our next speaker is Haley from, and she's going to be talking on quasi-polynomial time algorithms for free quantum games in bounded dimensions. Okay, over to you, Haley.
Yeah, thank you. Hi, everyone. Firstly, I would like to say thank you to organizers for giving me an opportunity to present my research in this great conference. And for the next 5 minutes, I would like to talk about my recent work on this quasi-polynomial time algorithms for free quantum games in bounded dimension. So the main topic of our work is characterizing quantum correlations of bounded dimension. And there were several motivations that we studied this topic. Firstly, it is a way to study quantitative advantages of quantum correlations with different dimensions. And it can be exploited as a dimension witness in semi-device independent quantum information processing tasks. So it has some practical importance as well. Also, the computational complexity of relevant problems is not really well studied yet. So this is why we studied this topic. In our work, we largely make use of non-local games, which is kind of a generalization of Bell inequalities. It is a way to mathematically formulate correlations between distant parties. So for the two-player case, Alice and Bob play this game against the referee. After the game starts, the referee chooses question Q1 and Q2 according to the question probability distribution pi and send them to Alice and Bob. And Alice and Bob have to provide correct answers A1 and A2 to the referee to win this game. And whether the answers are correct or wrong for given questions Q1 and Q2, it can be determined by this given rule function V. And after the game starts, Alice and Bob cannot communicate to each other, but they can exploit the previously established correlations between them to win this game. And in our work, we will particularly focus on a subclass of non-local games called free games, where the choice of the questions for Alice and Bob, Q1 and Q2, is not correlated. The reason why we focus on this subclass is because it actually gives us some advantage, and also because most of non-local games considered in physics are actually free games. So in non-local games, the advantages of different sets of correlations can be quantified by the maximum winning probabilities achievable by given correlation set. For example, when Alice and Bob are only allowed to use classical correlations, we can define this classical values omega c. And when Alice and Bob are allowed to use unbounded dimensional quantum correlations, then we can define this quantum values omega q, which is usually strictly larger than these classical values, which reflects that we can achieve better with quantum correlations. So quantum correlation has some advantage over classical correlations. And when Alice and Bob are only allowed to use fixed dimensional, for example, T by T dimensional quantum correlations, then we can define this dimension-bounded quantum values omega qt. So for example, when Alice and Bob are only allowed to share qubits or qubits, then this dimension-bounded quantum value is what you're looking for. And this is the main interest of our talk. However, these values are known to be very hard to compute, as you can see in this previous result. And for these dimension-bounded quantum values, there have been developed a few different hierarchies of SDP upper bounds for omega qt, and some of them provide a practical tool to compute this omega qt for some cases. But the best known worst case runtime guarantee for these algorithms is exponential in the size of the non-local gain. So what we did in our work is that we developed new approximation algorithms for computing omega qt of two-player free games with significantly improved running time. So more specifically, we constructed a new hierarchy of SDP upper bounds for omega qt, and then derived analytical bounds on the convergence speed of this SDP hierarchy using a mathematical tool called quantum definite theorem. And this directly gives us our second main result, that we gave an upper bound on the computational complexity of computing omega qt of two-player free games. In more details, to construct this new SDP hierarchy, we made a connection from the dimension-bounded quantum value omega qt to a variant of the quantum separability problem, where the optimization variables are additionally subject to additional linear constraints, and then employed the DPS hierarchy to develop this our new hierarchy of SDP relaxations for omega qt. And then we derived an appropriate version of quantum definite theorem for our setting to show the analytical convergence speed. And yeah, and this is the quantum definite theorem we derived. And to prove this quantum definite theorem, which was the main technical ingredients of our work, we exploited this new this information theoretic proof technique using quantum entropy inequalities. And then also as one of the key steps for the proof, we derived an improved version of the optimal distortion relative to quantum side information, which we think might be of separate interest to some people. And then this is our main contribution. We show that we can estimate omega qt, the dimension-bounded value omega qt of a two-player free game with T by T dimensional quantum correlations within a constant additive error epsilon with a semi-definite program of size this, where this A and Q denote the number of possible answers and questions of the game, respectively. And the important point is that for fixed dimension T, this complexity scales polynomially in Q and across polynomially in A, which is an exponential improvement on the previous algorithms. And our result can be seen as the quantum extension of the quasi-polynomial time approximation scheme for classical value omega c developed in these two papers before. So this was our results, and for more details, please watch the longer version of our talk. I'd like to thank my collaborators and thank you for listening. I'm happy to take any questions. So, yeah.
Okay, so thanks, Haley, for the nice talk.
So I have one question. Does your optimization technique generalizes to other optimization problems in quantum theory with finite dimension? So I don't know, for instance, the random access code or other tasks?
No, I think our optimization problem is kind of, yeah, we only consider this non-local game. So you want to just optimize this, you want to just get this dimension-bounded quantum value omega qt, and I think it's restricted that one. It cannot be generalized to any optimization problem with finite dimension. Sorry.
Yes, thank you.
Okay,
So
okay.
actually, I have a second question. I don't see any
Yeah.
other questions, so I ask.
Yeah.
So because before that, the technique I knew was this Navasquez-Vertesi hierarchy,
Yes.
in which you have this sampling method, which is not mathematically completely rigorous because you have to sample over a space. I don't know how much you know about it. So do you have like a sampling technique somewhere? I guess not.
No, yeah, I'm not sure what you refer to with sampling technique of Navasquez hierarchy, which yes. So I don't know what that is.
Okay. Yeah, I will.
Yeah, we didn't use any sampling technique here. It was mostly so the main thing is it is DPS hierarchy. So we could just convert this optimization problem omega qt to kind of this variant of quantum separate problem, and then we use this extendable states hierarchy to make approximate this quantum separability state set to construct this hierarchy, and that's the main tool we use. So there is no sampling ingredient in our method.
Okay, thanks a lot.
Yeah, sorry.
Okay, so if there are no more questions, then we thank the speakers of this session again. And yes, and then we can just quit the session. Thank you.
Hello, is my sound working?
I can hear you.
Okay, great. Do we know what order?
I don't know what
or
order.
anything? Okay.
I think yes. So Scott, you are talking first, and then
Oh,
Simon.
okay. All
Great.
right. Okay, just let me know when I should share my screen then.
Yeah, sure. I think we'll be starting soon. So it's like 1 minute to 5 o'clock. So we'll start at 5 o'clock sharp. Okay, and okay, and then I'll let you know, of course. Okay, so it's 5 o'clock now. So welcome to the first open session of this TQC conference. Okay, so we'll have 2 sessions. The second session will be on Thursday. Okay, and so today we have 2 speakers, so Scott Aronson and Simon Burton. Okay, so expected we will think will be shorter than 1 hour. So I think we will finish in half an hour, even less. Okay, and okay, so I guess that's it. So without further ado, so let's Scott, you can talk and start with your favorite open problems.
All right, well, thanks. It's great to be back in Riga, even virtually, and great to be at TQC. And so I wanted to talk about a few. I decided just yesterday to tell you about a few of my favorite open problems related to quantum query complexity. Let's do full page. All right. So I'll just go through, and then I'm happy to take any questions about them afterward. So all right, let me start with some basic ones that probably many people have heard of, but that I've wondered about for 20 years or almost 20 years, and that are still unsolved, despite all of the dramatic progress that there's been. Including just within the last few years in quantum complexity theory. So, there is the problem of QMA versus QCMA, where QMA is, what we can verify with a polynomial size quantum witness and polynomial time quantum computation to check it. And QCMA is the same, except that now the witness has to be classical. Okay, and so Greg Cooperberg and I in 2007 showed that there is a quantum oracle that separates QMA from QCMA. 5 years ago, Shelby Kimmel and Bill Pfefferman show that there is like a weird kind of classical oracle that separates them, a randomized permutation oracle. But we still don't, no one has shown that there is just an ordinary oracle problem, that has short quantum proofs for a yes answer, but does not have short classical proofs. And this is now that BQP versus PH, in the oracle setting is solved and so forth. This has really emerged, I think, as one of the great problems of quantum complexity theory. Another problem is there an oracle that separates QMA from QMA2, where QMA2 just means QMA, but where you get two quantum witnesses that are guaranteed to not be entangled with each other. Okay, for this one, we don't even have a quantum oracle that separates those classes at present. Now that's another problem that I love. So one more that I can't resist mentioning that goes back to the work that we did on the collision problem 20 years ago. A whole bunch of the open problems about the collision problem that we knew at that time, back in 2001, 2002, have since been answered. But one problem that remains wide open 20 years later is, what is the time-space trade-off for finding collisions? So, I give you a 2-to-1 function. We know that the best quantum algorithm for finding collisions in that function will take something like cube root of n time, where n is the size of the range. That algorithm also uses cube root of n space. And so we're asking, is there a trade-off? If we required the algorithm to use only log of n space, like Grover's algorithm does, then would it be forced to use more than cube root of n queries, like square root of n queries or something like that? And we still don't even seem to have the tool with which to address that kind of question. All right. Now, another that I can't resist mentioning is something that Greg Kuperberg and I raised in our paper in 2007, and which I later took to calling the unitary synthesis problem. Okay, and the question is just the following: is it true that for every n-qubit unitary transformation U, there is some oracle A, so some classical Boolean function, but which could be queried quantumly, such that it is easy to apply U given an oracle for A. Okay, so such that a BQP machine with oracle access to A could then implement that unitary. Okay, we originally asked this in the case where U is some Haar random unitary. Okay, but you could ask it about any unitary, and this might seem like a weird technical question, but it has just cropped up again and again. It crops up when you're thinking about quantum money schemes. It even crops up when you're thinking about the computational complexity of decoding Hawking radiation that comes out of a black hole, like in the analysis of the firewall paradox by Harlow and Hayden. Okay, so it crops up when you're thinking about the non-abelian hidden subgroup problem. Okay, so we're asking, for every unitary, is there some oracle that makes that unitary easy? It's easy to show that for every state, for every entangled state of n qubits, there is some oracle relative to which that state is easy to prepare. I could offer that as an exercise, but for unitaries, we don't know. I would conjecture that the answer is no, but again, we seem to lack the tools to prove it. All right, so my next set of questions is about the verifiability of quantum computations, which of course is a subject where there's been enormous recent interest and, and several recent breakthroughs, famously including the protocol of Urmila Mahadev. But I would like to ask about verifiability in the black box setting. Okay, and so maybe the most basic question that we could ask here, and something, one of the most basic questions about BQP, and the relation between BQP and classical complexity classes that is still open, even relative to oracles, is simply, is there an oracle relative to which BQP is not in IP? That is, relative to which there are BQP problems that have no interactive proofs. In the unrelativized world, of course, we know that IP equals P space, and therefore BQP is contained in IP. I'm asking about the black box setting here. Okay, and a clear candidate for a separating problem would be the correlation problem, which I introduced in 2009, and which Raz and Tal famously used just a few years ago to achieve their breakthrough of an oracle relative to which BQP is not in the polynomial hierarchy. Okay, I conjecture that that the same problem would also not be in IP relative to an oracle. But to prove that seems to require a new sort of circuit lower bound. Okay, for if you're fighting the polynomial hierarchy, you're talking about AC0 circuits. If you're fighting against interactive protocols, you're talking about circuits with average gates and max gates. And there is some work on such circuits. For example, a 1989 paper by Aiello, Goldwasser, and Hastad. But I have no idea how to lower bound the sizes of such circuits for the correlation problem. Okay, now a weaker thing we could ask for is there an oracle separation between BQP and what you could call IP-BQP, which is just the class of languages for which a quantum interactive prover, a BQP prover, can convince a classical skeptic, a BPP skeptic, that the answer is yes. So IP-BQP is a subclass of BQP. And here we're asking, relative to some oracle, is it a proper subclass? Are there things that a quantum computer can do, but for which it cannot prove the answer to a classical skeptic? And a candidate for that, I think, would be just the complement of Simon's problem, right? Where, a quantum computer, of course, can solve Simon's problem, can tell whether your function, let's say, is one-to-one, or whether it satisfies the Simon promise, given that one of those is the case. But if your function is one-to-one, then how would the quantum computer convince a classical skeptic of that, right? There is an interactive protocol for it, actually based on approximate counting, but not one that a quantum computer seems to be able to implement. Okay, so and another way to think about what we're asking is if you look at these celebrated protocols for verifying quantum computations, like Armila Mahadev's, or you could go even earlier to Broadbent Fitzsimons Kashifi, Aharonov Ben-Or Eban. Are these protocols inherently non-relativizing? Okay, and that's such a basic question that it's astonishing that, as far as I know, it is still open. Okay, the protocols don't obviously relativize, but no one has actually constructed an oracle relative to which these protocols provably don't work. All right, my next problem, my next open problem concerns the famous glued trees algorithm, which was published by Andrew Childs, Ed Farhi, and others in 2002. And this was the first provable exponential quantum speedup via a quantum walk algorithm. Okay, and so they constructed this funny graph that I just drew for you here called the glued trees graph. And they showed that if you start at the start vertex, a quantum walk can reach the end vertex with 1 over polynomial in n probability after 1 over polynomial in n time, where n is the depth of these binary trees, which are sort of glued together by a random matching. Whereas they showed that any classical algorithm that is limited to just querying the graph will need exponential time to find the end vertex if you started at the start vertex. Okay. Now the question that I ask is: suppose you not only want to find the end vertex, but you actually want to find a path from the start vertex to the end vertex. So something like this. Okay. You want the entire path. Well, the quantum walk algorithm will not give you a path, right? Because it's just doing this coherent tunneling process. if you measured it to see where it was, then you would destroy the interference, right? So I'm asking about, this sort of, this is almost like a complexity theoretic version of quantum complementarity, asking, if you actually want to see a path, then is that hard even for a quantum computer to find? Will that take even a quantum computer exponentially many queries? I love this question because of its sort of conceptual import. All right, now my next to last question is about comparing two different types of quantum queries. Okay, so the conventional kind of quantum query would take basis states, let's say, of the form X and A, where X is an input and A is an answer register. And we would take our function that we're querying, say f of X, and XOR it into the answer register. Okay. Now there's also, if f is an injective function, then we can also consider this type of query that just takes X and overwrites it, replaces it by f of X. Okay, now we know that there are cases where this kind of query can be exponentially more powerful to have than this type of query. And in fact, the collision problem provides, or a variant of it, provides precisely such an example. That was one of my original motivations for thinking about the collision lower bound. Elham Kashifi pointed the connection out to me. Now, what I'm asking with this question is, what about the other direction? So are there properties of F that you can learn exponentially faster if you have the conventional type of query, this kind, than you can if you only have the overwriting kind of query? Okay, now I'll give you a candidate that I think would show that. Take F to be just some like the assignment function, just some function where we know that there is an exponential quantum speedup, and then a whole bunch of random garbage that is just completely unrelated. Okay, then with the normal type of query, we can just query twice and we can uncompute the garbage, and then we just get F, and then we can solve Simon's problem. With this type of query, though, we can only go one way, right? So we get the garbage, and the idea is that the garbage is, effectively reduces the query to being classical, right? It's as if the register has been measured, because we just, we don't know how to get rid of the garbage, but I don't know how to prove this. All right, my very final question is about, is there a sort of query complexity version of the Tsarelson inequality, right? That says that quantum mechanics can only do so much better than, a classical model and not more. So here's a concrete question. Let's say that we've got a Boolean function F, that we can make queries to. Then, one of the basic things we can do is we can do Fourier sampling. So we can sort of sample string Z with probability that goes like f hat of Z squared, right? The square of the Zth Fourier coefficient of F. And this something like this is exactly what was done in the quantum supremacy experiments. The boson sampling, random circuit sampling, what Google and USTC have now done. This is kind of like the query complexity version of that. Okay, now the question that I want to ask here is, what if you want to do even better than what the standard quantum algorithm would give you? So, the standard quantum algorithm, if you calculate it, if I get like K samples, then, each one will be have a Fourier coefficient of about 3 over 2 to the n on average. Now, what if I want even larger Fourier coefficients than that? Is that hard even for a quantum computer? Will even a quantum algorithm need exponentially many queries to F? And so, could we imagine some post-quantum model of computation that can do even better at this quantum supremacy experiment than a quantum computer itself could do? And then, what could we say about that post-quantum model? Okay, so those were my questions for today. So thanks for listening, and I'm happy to take any questions about the questions. Oh, I see from an anonymous attendee, do I think that the oracle separation between BQNC and BQP will be helpful for approaching an oracle separation between BQP and IPBQP. I mean, to me, those seem like very different questions. You know, I mean, I was delighted that we do have now an oracle separation between BQP and actually BPP to the BQNC, which was another of my favorite open problems for a very long time. And, you know, my postdoc, Naihui Chia, was then involved in solving it a few years ago. You know, IPBQP seems to me like a very different question, you know, but, you know, I think it might take some sort of circuit lower bound type of technique. Yeah.
Okay. Okay. Thank you, Scott.
Sure. Sure. No problem.
Yeah. So please ask more questions. So we still have a lot of time. So feel free to ask more questions. Okay. And so I have one question myself. So about this time space trade-off. So about the collision thing. So so I've been thinking about this, and I think one problem is like so many types of memories that you can use. For instance, you can use only quantum memory, or you can use classical memory. And another thing, if you use this standard way how you get like a quantum algorithm, so you postpone all the measurements to the end, so it can actually blow up the space complexity quite a lot. So what do you think like would be more interesting, like to get this kind of trade-off in this standard model, or try to get something in using the classical and allowing measurements in between?
Yeah, I mean that's a very good question. I mean, my understanding is that right now we lack even the weakest result that you could ask for here, right? So even if we said that the memory has to be classical only, you know, as it is in the algorithm of Broussard, Hoyer, and Tapp, right? We still don't have a lower bound, a trade-off result. In fact, the only time-space trade-offs that we really know in quantum query complexity are for problems that have a large number of output bits, right? Such as sorting, for example. So I would be interested in any result that advances the state of the art. You know, now you know, you could say, you know, arguably the most interesting would be if you could look at something like Ambianus's algorithm for element distinctness, and you could say that even assuming a large memory, you know, the memory has to be quantum if you want to get, you know, an n to the 2/3 algorithm, right? If you could say that, you know, even with n to the 2/3 classical memory, you cannot do it, right? Then, you know, that would sort of really explain why that algorithm is the way it is to a great extent. But, you know, of course, I would be happy with any result here that with any type of memory that goes beyond what we already know.
Okay, so thank you very much for the answer, and thank you very much for your open problems. And I think we don't have any more questions at the moment. So if you have questions to Scott, just ask them offline.
All right, let me stop the share.
Then we move to our second speaker of today is Simon Burton. So when you're ready, just share the screen and start talking.
Okay. Can you see my mouse?
Yes.
Okay, great.
It's kind of really small, but you can see it.
Yep. Yeah, so please interrupt me if you know more than me about something or have a question or something. I'll try to just take about 5 minutes. And I'm just focusing on one problem here, which is, can we find a self-correcting quantum memory in 3 dimensions? So this is a Hamiltonian that protects its ground space from an environment at some low temperature. And we can do this easily with a classical memory. This is how our computers work, but it's much more interesting, the quantum version of this question. And we know we can do it in 4 dimensions, and we're pretty sure we can't do it in 2 dimensions, but the 3-dimensional case is totally open. as far as I know. And right now, I'm just going to focus on one candidate possible Hamiltonian, which is known as the 3D gauge color code Hamiltonian. And I don't know how the actual criterion for being a quantum memory is. It's not like it's exactly pinned down, but one thing that really seems important is that the Hamiltonian must have a gap, a finite gap that doesn't go to zero between the protected space and the excitations. And this is how I think about what happens when the Hamiltonian doesn't have a gap. You get these very low frequency vibrations that come in and just destroy your quantum, you destroy your encoded information. And I always end up thinking of the Tacoma-Narrows Bridge. It's like this big long thing that starts wobbling, and the longer the bridge is, the longer these wobbles become. That's just my intuition for what gapless excitations look like. And one reason why I really get excited about this problem, and why I'm not talking to condensed matter theorists, is that there's a kind of a Rosetta Stone or a dictionary between two different languages. And one is a condensed matter theory language, and the other one is quantum codes. And a lot of these concepts translate between the two languages. So this is what we're trying to do, is take the ground space of the Hamiltonian and use that to store the information. And errors in the code correspond to excitations in the Hamiltonian. The codes I'm talking about today are known as CSS codes, and that means the Hamiltonian is stochastic. And when the generators of the code all commute, you get a frustration-free Hamiltonian, and these correspond to stabilizer codes. And those are easy to diagonalize these Hamiltonians and see that they have a constant gap of 2. When the generators don't commute, these are known as subsystem codes or gauge codes. And this is much more tricky, working out what the gap is. The 4-dimensional quantum memory we've known about this for 20 years. And there's a connection here between the single shot error correction of the 4D code and being a quantum memory. And this was something similar holds for the gauge color code, this single shot error correction property. And the question is, does that connect to the quantum memory property in terms of the condensed matter picture? And for example, here's another example, the 2D Bacon-Shaw code corresponds to, in condensed matter theories, the 2D quantum compass model. And this thing has gapless excitations. So it's not a good quantum memory as the code gets bigger. And I guess my question is that the stabilizers of this code get bigger and bigger. And this is part of what I'm proposing as an open problem is, do these extensive stabilizers correspond to gapless excitations? Because in the 3D gauge color code, the stabilizer generators are bounded. They don't get bigger and bigger as the code gets bigger. Right, so that's one proposed conjecture. Who knows if it holds on the nose? Maybe there's some other requirements over here, like locality or something like that. And just to give you an idea of what these gapless excitations look like in the quantum setting, this is kind of like quantum Tacoma-Narrows Bridge model. It's a double well Hamiltonian, and I don't know if you noticed already, but my Hamiltonians are negative of the negation of what people usually write down. So yeah, so the double well potential has ground states that look kind of like this. The ground state tries to live in the two wells. Here it's at 1 and 12, and then it exponentially dies away from the wells. And you can show that this model is gapless by using the symmetry of the system. You perform a cut in the middle and you reflect half of the wave function. And that gives you an orthogonal state, which is almost a ground state. The only place it's not a ground state is along the cut here. So you can kind of squeeze the eigenvalue of the excitation down towards the eigenvalue of the ground state. Let me just show you quickly what these gauge color codes look like. So here I've got a picture. The qubits live on the vertices of this picture. The faces, or the qubits of the faces, are where the gauge operators. So that's the terms of the Hamiltonian, or the faces of this model. And the colors have to do with the combinatorics. It's kind of a distraction, actually. That's a separate thing. But each face contains an operator for the Hamiltonian. And then the cubes of the model are the stabilizers. So those end up being, what do the condensed matter people call this? Invariants or invariants of the Hamiltonian? There's a word that the condensed matter people use for operators that commute with the Hamiltonian. And this is the sequence of three examples of this code going up to 175 qubits. I did some work on diagonalizing these Hamiltonians, and this is a comparison between some different models. This is the 2D compass model down in the lower left, and then the gauge color code model is here, is the brown one. And I did some more work trying to work out how the size of the stabilizers correlate to the gaps of these excitations as well. But it's totally open as to whether this model, if the gap here goes to 0 or not. So that's my open problem for today. Thank you.
Okay, thank you. Thank you very much, Simon. So for your for the open problem, and so far I see no questions, neither in the chat nor in Q&A. So
okay,
if you have any questions, I'll just please ask. So I have one question in the meantime. So maybe some other will show up. So I'm not an expert in this error correction and everything. And so my question is, like, you say that like 4D is possible and 3D is not known to be possible. So is it the case that like 3D is some kind feasibly feasible in our universe, three-dimensional, and like 4D is not feasible, or it is not the case? So why are you interested in 3D exactly?
Yeah, well, there's the possibility that such a thing could be engineered in 3 dimensions. That's true.
Yeah, so and 4-dimensional is like clearly not possible.
2 dimensions, we're pretty sure it's not possible under a lot of circumstances for a lot of different codes. Yeah.
Okay, thank you. And okay, I still see no questions, so I think that's fine. Thank you again. Thanks for both the speakers of this open session. And okay, so this ends our open session and open problem session. And so if you have any other questions that you maybe come up and maybe you have something to discuss, so then you can do it during our virtual coffee break. That is like, let me just, it's TQC 2021 LV/coffee breaks. So you can continue discussion there, so if you wish. And but for now, this open session is closed, and we will continue with the next session after the break. Okay, thank you again for the both speakers and for everyone attending.
Bye-bye.
Bye-bye.
Hi, everybody. Let's get started. So welcome to the first evening session of TQC 2021. Our first speaker will be user Yakar Yilmaz, who will be telling us some new results about quantum log space.
Thank you. Hi, everyone. I am Abuzar Yakar Yilmaz. I am a researcher in Andris Ambainis group. They are organizing this conference. I am also affiliated with Keyword Association. This work is jointly with François Legal and Harumichi Nishimura from Japan. And I will present our, let's say, newest result about quantum logarithmic space using the post-selection ability. I also would like to thank the program committee to select our talk, and also the organizing committee for all preparations. So I guess post-selection is one of the most interesting topic in quantum complexity theory. In 2005, Aronson showed this equality about the polynomial time classes. Unbounded error probabilistic polynomial time is equivalent to bounded error quantum polynomial time using the post-selection. And in this work, we show the same result for the logarithmic space computation. Here, time bounds are also polynomial. So in the presentation on YouTube, you will see the full details. Here, I will shortly mention some key parts. So for our proofs, we use the Turing machines. When you work with the space-bounded computation, I mean, traditionally, you separate input space from the work space. So you have a separate tapes for them. Input tape is read-only, and then you can work, you do your read-write operations on the work tape. Here you see the schema of a probabilistic Turing machine. And we just modify this definition by adding a quantum tape, and this quantum tape can have a multiple heads, but of course it should be fixed. Then you can see also this quantum tape as a circuit. We can access many qubits or qubits, how you define it. And then we apply our quantum operators. And we also allow, of course, intermediate measurements to follow our results here. And what about post-selection? It's kind of like a conditional probability. You have a set of outcomes, and you just say that I just focus on this predefined set, and I will discard the rest of them. So this is a kind of unrealistic, let's say, ability. But still, you are looking for bounded error algorithms, so the balance between this post-selected part should be nice, let's say, to have a well-defined algorithm. So usually in Turing machines, we have accept and reject state, so we also define another halting state. You can just kill the computation there and also discard. They don't have any effect on the decision, your final decision. So in our case, all computation must terminate with probability 1. Also, this post-selecting part must have a non-zero probability. Otherwise, we may not normalize to give the final decisions. So we have two sides for our proof, show the equality. This part is little trivial. Post BQP is in the PL. Basically, when you enter the post-selecting part, you just restart the computation from the beginning. Then this algorithm turns out to be a like bounded error algorithm, but instead of polynomial time, you spend exponential time, and this is already in the BQL, like unbounded. It was shown before, unbounded error quantum logarithmic space, and we already know that it's equal to PL. So this part is part of the proof is kind of trivial. This part was non-trivial, and we have a proof by construction. And we have 3 steps. First of all, the given PTM, we just reformulate it like it's a log depth circuit, probabilistic circuit, and its computation can be constructible in logarithmic space. So we kind of create a probabilistic circuit, and by using polynomial time, we can just simulate the same computation. Because in this way, we can simulate this probabilistic circuit as a quantum circuit. And then at the end, we will have this exponentially small acceptance and rejecting probabilities. And then we used a trick proposed by the Aronson, and then we end up with a bounded error algorithm. So I will give just very quick details. So we have a probabilistic circuit, and the idea here, any configuration of a PTM can be log size. So basically, we can create a circuit with log depth. And when you have all the configurations, simply you have a probabilistic operator applying the same operator n to the k times here, n to the k is the time bound. Then in this way, you can have a mixture of these configurations. But each operator is also mathematically we can apply once, but to let's say implement it on a log space, we really use many dummy layers. So if we have n different configurations, then it has really n parts. And each part, we just check currently our circuit is in the configuration J or not. And if it is in this configuration, then we also implement the transitions. We will go in one step. And for each this check and implement, we still use sequentially many gates. At first, you can easily build them with the 4 bits, and then we can also decompose them. At the end, you have a quite, but still polynomial length circuit, and you use only 1 or 2-bit gates. And then you can replace these probabilistic gates with the quantum one. Let's say their size is 4 times 4, and you can use 2 ancilla qubits each time. For each such operator, you can construct a unitary matrix. But of course, for this, you use some extra entries, etc. But at the beginning, you always start in state 0 here. Then you can apply this unitary operator, and then you make the measurement. Basically, here is your operator. Here you use some other entries to make this unitary matrix. But basically, only this part is implemented because you are in the 0, 0 in the ancilla qubits. And then when you observe also in the other parts in this ancilla qubits, you discard them. So with some probability, always you implement this operator. And in this way, in each step, you always continue your computation and implement exactly this probabilistic operator with some probability. And with the rest of the probability, you just discard the computation. But at the end, with exponentially small probability, you achieve all the computations. And in the last step, I think I also have don't much time. So we put like quantum state in this way. And we know that if you are, if the input string is in the language, then you are always on the unit circle 4th quadrant. Otherwise, you are in the 1st quadrant. Then you make a measurement in base of plus and minus states. So we use here the Aronson trick. So we also multiply the second entry with all possible power of 2's. We know that each time, if you are member, always the probability of accept is more than probability of reject. But at least once there is an error bound, then we also execute polynomial time our this construction, and then we obtain a bounded error algorithm. We also have some additional results. You can check the paper for details. I think my time is also run out. Sorry, I use a whole 10 minutes. Yeah, it should be a little shorter.
Yes, the time is up. So if you could wrap up. I think we have time for one quick question from UPAM Blue.
Does it depends on the size of? We have a bounded error at the end. It's not like some polynomial or just like 1 divided 3, let's say, and 2 divided by 3. Clean bounded error. So I think I'm done. Yes.
Yes, and out of time. So thank you for the great talk. Again, from the second presenter, Marcel Dalagnol, who's going to tell us about quantum proofs of proximity.
Okay, so thanks for the invitation. Thanks for the introduction and everyone for being here. So Marcel and I'm going to talk about quantum proofs of proximity, which is joint work with Tom, Shabayan, and Justin. The short talk is divided into 3 small chunks. I'll first introduce the computational model that we've been working with. Then I'll talk about an algorithm that is somewhat similar to the algorithms that we construct, but is simpler and rather illustrative of what we do. And then at the end, I'll just mention briefly our results. Okay, so for the model, I'll first start with the familiar notion of QMA, which is the set of all languages that are decidable by a polynomial time algorithm that we'll call the verifier, when it receives help from an all-powerful but untrusted prover P in the form of some quantum state. So formally, this is what it looks like. It's kind of a mouthful, but the important things to see here is that if the string is in the language, then there exists a proof that convinces the verifier of this fact. Whereas if the string is not in the language, then no proof can do that. And in this third setting, we allow the verifier to run in polynomial time. But of course, it's interesting to think about languages that are tested by, or they're decided by efficient verifiers. Let's say those that run in quasi-linear time. And this is indeed an interesting class of languages. But the one we study is that of super efficient verifiers, those that are running even less time than it takes to just read the input stream. And of course, in this model, this becomes trivial. But if you look at this through the lenses of property testing, then this does become an interesting and rich class. And there are basically 2 differences here. The first one is that now the verifier has query access to its input string rather than explicit access to it. And we also have to relax the notion of what it means to decide a language. Now, the verifier is only required to reject strings that are far from the language rather than every string that is not in it. And indeed, we can, there are interesting protocols with sublinear proof complexity and sublinear query complexity. And in fact, if either of those become linear, this becomes trivial in another way. So this is indeed sort of the right model for sublinear computation. Okay, and sort of the main protagonist of our work is the class QMAP for quantum Marilyn Arthur proofs of proximity. And this is parameterized by these 3 values. So P is the proof complexity, that's the length of this quantum state the verifier receives. Q is the query complexity, and epsilon is a proximity parameter that measures from which point on is the verifier required to start rejecting. Okay, so I'll leave that aside for a moment and now talk about a problem that doesn't really have anything to do with property testing, but is similar to some algorithms that we construct in our work. And the problem is very simple. Given some input string X, we want to verify if it has even parity or not, and we're allowed to receive some small untrusted proof to do that. It turns out that, like, classically, there isn't really much we can do since parity is such a sensitive function. We can't do much better than just read the entire input string and compute parity on our own, even without a proof. Now, quantumly, there is something non-trivial that we can do. And I'll explain this by means of a randomized algorithm, one that doesn't bias much in comparison to the deterministic one, but as we'll see, if we combine it with some quantum techniques, then it does give us something non-trivial. So the algorithm goes as follows. If we receive a proof of, say, length 3, then we divide our input string into 3 blocks. So for example, this proof claims that the parity of the first 2 blocks is odd, and the parity of the last block is even. Now, what the verifier will do is it'll just sample some block uniformly at random, read all of the bits in that block, and then check that the parity of the block corresponds to the parity of the proof. So in this case, the verifier would accept because both of them are odd. But if you had queried, say, the last block, then it would see that the block has odd parity, but the proof string claimed it had even parity. And in that case, it would reject. Okay, but if the verifier, if there's only, if only one block has some error, then the verifier detects that with a tiny probability. But now we can use the technique of amplitude amplification that allows us to boost the probability of detection without increasing the query complexity by too much. So if we just plug in a proof length of n to the power 2/3 in the previous algorithm and apply amplitude amplification, we do indeed get a query complexity that is also n to the power 2/3. Okay, so now I'll just quickly mention our results, and they come in sort of two groups. The first one is that a similar strategy to this one that works for parity works for every property that we call decomposable. And decomposability is roughly this structure by which instead of reading an entire, testing an input string, a big input string, we can test many smaller substrings. So with parity, that is the case. You can compute the parity of many smaller substrings to find the parity of the large one. So any property that has a structure that is similar to that allows for an efficient quantum proof of proximity. And this includes a host of interesting properties. The second group of results is so we begin to sort of chart the landscape of complexity classes that surround this notion of quantum proofs of proximity. In a few separations, but I like to highlight just one of them, which is separation between classical proofs of proximity and quantum testers. And this is via a reduction from communication complexity, which was, in fact, a problem that was raised in Montenero and de Wolf's survey, and we're able to exploit that to show the separation. Okay, so I guess I'm about running out of time. I'd just like to mention the one sort of obvious open problem that we left here, which is what if we add interaction? So this quantum proof of proximity is non-interactive. What happens if you allow prover and verifier to communicate back and forth? And in fact, there is a very concrete question that we can ask, because there is a general purpose classical algorithm classical protocol that tests a wide range of languages. And it would be interesting to see whether a quantum protocol can beat the best known classical one. Okay, so that's it. Thanks for listening. And if you're interested, I invite you to either watch the long talk or ask any questions. Thank you.
So I think we have time for one quick question if someone wants to ask. I don't see anything in the chat right now. Well, then I think we should move to the next speaker if we could. So thank you very much, Marcel. Great talk. All right, up next we'll have Noel Anderson telling us about leveraging unknown structure in quantum query algorithms. So whenever you're ready to start.
Okay, I think hopefully you can hear me now. Is that working?
Yes, we can hear you.
Okay, great. So we looked at span programs using the quantum query model. So in the quantum query model, we're given an input string, and our goal is to evaluate some function of that string. We're given the input string using a quantum oracle, and each application of this oracle, which is a quantum unitary, allows us to learn one bit of the input string. The number of calls we make to the oracle is called the query complexity, and the query complexity is basically the runtime. So if we have to learn less information about the input string, we can evaluate f of x faster. Also, not all inputs require the same query complexity or runtime. Some inputs are easier than others. So why did we look at span programs? Span programs are useful for designing quantum query algorithms because for any binary function over some specified domain X, span programs allow us to create a quantum algorithm with optimal worst case runtime. So by focusing on span programs, we don't lose any generality. So span programs minimize the runtime for the hardest inputs. The problem with this is that until our result, span programs had to be run for the worst case runtime. So even if you knew that there were some easier inputs, you had to run for the worst case and couldn't take advantage of the easy inputs. A number of previous results had shown that if you were promised that you had an easy input, you could run for shorter. Our result removed this promise and allowed us to get close to optimal runtime up to some log factors for all inputs within the domain, not just the hardest inputs. So how did we do this? We modified phase estimation, which is the key procedure in span programs. Phase estimation takes some unitary and some eigenstate of the unitary and allows us to estimate the phase that applies to that the unitary applies to the eigenstate. The span program model tells us how to construct a unitary based on the oracle and create some eigenstate. Then if f of x equals yes, then phase estimation will return a phase of 0. And if f of x equals no, then phase estimation will return a phase that is not 0. The precision that we run phase estimation to determines the query complexity. And so what we did is we reduced the precision. We were able to show that yes instances were still extremely unlikely to return non-zero phases, but easy no instances still gave non-zero phases. Hard no instances could give any phase. This meant that if we got a phase of 0 from phase estimation, we could f of x could be yes or no, and we would have to run longer. But if we got a non-zero phase, we could be extremely confident that f of x equaled no. We then use a negation procedure to construct a span program for the negation of f of x. The negation procedure preserves query complexity for each instance. This allowed us to also catch easy yes instances. We then run the entire algorithm for exponentially increasing runtimes, which allows us to get almost optimal runtimes up to the log factors. And we can stop early rather than having to run for the worst cases. We also developed a modified algorithm to tackle state conversion. However, state conversion presents a number of problems because we never actually make a measurement, so it's really hard to tell whether we run for long enough. We developed a number of testing procedures to figure out what the appropriate runtime was for each instance, but it got a bit more complicated. The general procedure was similar to what I just outlined. One issue we encountered was that the error scaling in our modified algorithms wasn't great. One possibility that seems promising is that we may be able to use fixed point methods to get rid of some of this error scaling. And yeah, thank you.
All right, well, we have plenty of time for a question. If anyone has a question, they can ask through the chat or well, if there's anything you would like to add, Noel, for the last extra minute or two.
The other thing that we're looking at is whether previously the span programs had to run for the worst case, so there was no possibility that we could see like average runtime improvements, but now because we were able to get the runtime to be dependent on the entire domain of the function, we could see average runtime speedups. So that's another thing we're looking at, of whether, depending on what the distribution of instances is over the domain, we may see average speedups rather than just having to use the worst case. So, yeah.
All right, great. Thank you. Very interesting talk. Oh, we do have a question here from Dave Javuda Barra, who asks, is your modified phase estimation algorithm, what is the dependence of query complexity on the precision? Is it the same as in the original version?
Yes. So I guess I wasn't sharing my video. So in the phase estimation for the span programs, and the function evaluation, we basically just turned down the precision, and then we're able to show that even with the turned down precision, we could still get good results for the easy no instances. For the state conversion, everything got way more complicated. So there was just like a lot more dials that we had to fiddle around with.
So we have another question from Arjun Cornelesen, who asks, do your techniques carry over immediately to speeding up the approximate span program algorithm?
I'm not sure. And that's a good question, and I don't know.
So I think we have time for one more quick question, if anyone else has. Otherwise, we can move to the next presenter. So thank you again, Noel.
Thank you.
So next we'll have William Kretschmer, who's going to tell us about quantum pseudorandomness and classical complexity. So whenever you're ready to start with.
Hold on a sec. This is not working. Let's try again. All right, there we go. Okay, can you hear me?
Yes, we can hear you and see you.
Good. All right, so yep, this talk is about quantum pseudorandomness and classical complexity. And I'll start by kind of just summarizing what this work is about. So the main objects of study in this work are something called pseudorandom quantum states, which I'll sometimes abbreviate as PRSs. And intuitively, you can think of these as being computational approximations to the Haar measure. So just as pseudorandom generators give rise to sort of computational approximations to the uniform distribution, so pseudorandom states are sort of like computational approximations to Haar random states, so uniformly random unit vectors that are computationally indistinguishable. And I guess the main question that I try to answer in this work, or I try to better understand, is where do pseudorandom states fit in the complexity theoretic landscape? And in particular, how do they kind of relate to complexity classes? What assumptions, under what kinds of assumptions do they exist? And those sorts of questions. And as we'll see in this talk, we kind of don't understand this as well as we would like to, and it sort of motivates even more questions than it answers, perhaps. So I'll first tell you just a little bit about why you should care about pseudorandom states. So there's a few motivations. One is just that kind of the most obvious one. These are a cryptographic primitive, so they can be used for cryptography, so things like quantum money. Maybe there's other applications that we don't know of yet, because these were defined pretty recently. Another fairly obvious application is that these can be used in like quantum simulation algorithms. Let's say you're taking some average over a generic looking Haar random state, maybe something involving like thermalization. And in that case, it turns out that pseudorandom states, these PRSs, can be more computationally efficient than, say, information theoretic approximations to the Haar measure. And then finally, there's what I think is maybe the most interesting recent development relating to pseudorandom states, which is that a recent connection that was established by Bolin, Pfefferman, and Vazirani between PRSs and some fundamental questions in black hole physics, in particular in the ADS-CFT correspondence. So basically, there's some questions that seem to require tools from computational pseudo-randomness of quantum states in order to answer. So I would say between all of these, we definitely have good reasons to want to understand pseudo-random states. And so, well, okay, so what do we know about pseudorandom states? Well, turns out one of the only things we know about pseudorandom states is how to construct them. And Ji, Liu, and Song in the paper where they first introduced PRSs, what they showed is that if quantum secure one-way functions exist, then pseudorandom states also exist. So this is, I think pretty good evidence for the existence of pseudorandom states. I would say quantum secure one-way functions is something that most people are willing to believe in. This is certainly a much less strong assumption than, say, hardness of specific problems like factoring or learning with errors that we tend to need for public key cryptography. But what I was sort of interested in for this work is actually looking in the other direction, which is assuming pseudorandom states exist, what else has to be true? What other, I guess, cryptographic primitives or complexity theoretic implications are there of pseudorandom states that are worth knowing about? And in fact, this was even an open problem that was posed in this paper where PRSs were first introduced. They asked, is there a converse to this theorem? So assuming pseudorandom states exist, does that imply one-way functions exist? And in some sense, the main result of this work is kind of a negative answer to this question. So what we do is we construct an oracle relative to which the following things hold. One is that pseudorandom states exist relative to this oracle. And the other is that BQP equals QMA relative to this oracle. And this BQP equals QMA implies, well, not only does it imply that there are no quantum secure one-way functions, but it actually kind of implies that there's no quantum secure cryptography at all. And this is just because most cryptography can be broken in the complexity class NP, and NP is contained in QMA. So if BQP equals QMA, then all these problems can be broken efficiently by a polynomial time quantum algorithm. So in some sense, this is saying that actually pseudorandom states are potentially a much weaker cryptographic primitive than basically anything else you could possibly think of. In the sense that there's a black box separation between the existence of pseudorandom states and basically, like I said, all other classical cryptography. There is the caveat here, this is sort of inherently a quantum oracle. So it would be nice to show this same result relative to classical oracle, but that's something we don't know how to do. The second main result in here shows an upper bound on, so, well, you can think of it as being an upper bound on the power that you need to break pseudorandom states. And what this shows is that if you can solve sharp p-complete problems, so if BQP equals probabilistic polynomial time, then pseudorandom states do not exist. And moreover, this also holds relative to all classical oracles. So that's essentially the two main results in here that I'll mention. There's some other results that I sort of don't really have time to talk about. If you're curious to see those, I talk about those in my offline talk. One thing I'll also mention is that I've only talked about pseudorandom states so far, but actually most of the results in this paper also hold for pseudorandom unitaries. So you can essentially just drop in everything I said about pseudo-random states, and pseudo-random unitaries holds true also. And I guess I think that's about everything I had to talk about. So if there's any questions, I'd be happy to answer them.
Indeed, we have plenty of time for questions. I don't see any in the chat at the moment, but if anyone would like to ask a question, now's a good time.
I mean, if not, I can also try to think of other points to mention.
By all means, please add what you can.
Yeah, I guess, I mean, maybe in terms of, interesting follow-up questions and open problems, for me, the most interesting one is whether you can solve the same problem relative to a classical oracle instead of a quantum oracle. But there's some other ones, like, can you sort of give some, I don't know, can you like instantiate some sort of oracle that behaves like this in the real world? Or maybe what I'm saying is, can you construct pseudorandom states via some assumption that does not imply some separation between BQP and QMA in some non-trivial sense? Is there a question in chat?
Yes, we do have one question from Noel. If he wants to unmute himself.
I was just wondering if you had mentioned there was a connection with black hole information theory.
That's right. So this connection to ADS-CFT, this was, I guess, established a couple years ago, where they showed that well, okay, I guess I don't really know enough about ADS-CFT to explain this using the right language, but basically they show that there's some this wormhole growth paradox where if you look at things from the, I guess, the ADS perspective, there are certain things that should be computationally distinguishable, whereas from the CFT perspective, they should be computationally hard to distinguish because they should look pseudorandom. And so there's some, I guess this suggests that either there's a exponential computational complexity in the ADS-CFT dictionary, or what was it? Otherwise, they conclude that the quantum extended Church-Turing thesis must be false, or something like this. I guess whether this work has any direct implications for that is not entirely clear, but I'd certainly be curious to know whether any of these oracle separations can be interpreted from an ADS-CFT lens.
Thanks.
Okay, I think we're out of time. So thank you again, William. Great talk.
Thank you.
Up next, we have our final talk for this session by Gregory Rosenthal. You can start sharing your screen.
You guys can hear me?
Yes, we can hear you and see you. And he'll be telling us about the complexity of approximating parity for constant depth quantum circuits. Are we ready to start?
Okay. So first I'll define the model of computation. QAC0 circuits are constant depth quantum circuits with arbitrary 1-qubit gates and so-called generalized Toffoli gates of arbitrary arity, which act on the standard basis by flipping the target qubit if and only if all of the control qubits are 1. More generally, we can consider QAC circuits which are not required to have constant depth. So QAC0 circuits are quantum analogs of AC0 circuits, meaning constant depth Boolean circuits with unbounded Fandin and OR gates and NOT gates. But it's not actually trivial for QAC0 circuits to simulate AC0 circuits. The reason for this is that AC0 circuits are implicitly allowed to fan out for free, meaning that at no cost, they can create arbitrarily many copies of the input bits and of the outputs of gates, whereas QAC0 circuits are not granted this ability axiomatically. So for QAC0 circuits to simulate AC0 circuits, we would like them to be able to compute the fan-out transformation pictured here, which acts on the standard basis as follows. It has one control bit, that's like a 0 or 1. If it's 0, it does nothing. If it's 1, it writes a 1 to all of these ancilli initialized to 0. So this raises the question, is fan-out computable in QAC0? Preferably if it's n-qubit fan-out that we would like to compute, then we'd like to do this in size polynomial in n, but it's even an open problem whether this can be done in arbitrary size exactly when n is sufficient, when n is arbitrarily large. And it's known that the n-qubit fan-out transformation is equivalent to the n-qubit parity transformation up to conjugation by Hadamard gates. So the question of whether fan-out is in QAC0 is equivalent to the question of whether parity is in QAC0. And remember, we can't just use the usual exponential size constant depth circuit, AC0 circuit for parity, because again, that uses fan-out implicitly, at least at the inputs. And for comparison, a famous result of Hastad is that parity cannot be computed in AC0, or it requires HP0 circuits of at least exponential size. And finally, for added motivation, not only can QAC0 circuits with parity or fan-out gates compute parity, but they can also compute the majority function as well. So in this slide, we talk about the previously known results and then the results proved in the current paper. Here, we define size and depth as counting, or size is the number of multi-qubit gates, i.e. the generalized Toffoli gates, and depth is the number of layers of multi-qubit gates. And this is analogous to how in classical circuit complexity, it's customary to not count the NOT gates to size and depth and to only count AND and OR gates. So first, there's an easy log depth linear size upper bound. This is explained more precisely in the full version of the talk, but it's not very difficult. There's also a lower bound of this form, which says that, for example, if the number of ancilli is sublinear, then you require at least super constant depth to compute parity or fan out. But this doesn't give anything when the number of ancilli is linear or greater. And finally, it's known that depth 2 QAC0 circuits cannot compute parity or fan out exactly when n is sufficiently large. Now, in the current paper, we prove 4 main results. First, there is in fact a constant depth QAC0 circuit that approximates parity arbitrarily well. In the full version of the talk, I explain exactly what I mean by approximation, but for now, just think of it as worst case quantum inputs. So for example, in depth 7, it takes exponential size, and more generally, there's a size depth trade-off similar to that of classical AC0 circuits computing parity. We also prove a lower bound. This lower bound is explained more precisely in the full version of the talk. Basically, what we do is introduce a certain subclass of QAC circuits that generalizes the circuit from our upper bound, and prove that our upper bound is tight with respect to circuits from this subclass of QAC0. So new ideas are needed in order to improve on the upper bound. Then we prove that depth D QAC0 circuits of size at most 0.23 or so, some constant like that, times n over d plus 1, require or cannot approximate parity with much better than a 1/2 approximation, regardless of the number of ancilli. And this 1/2 here is tight. And finally, we improve the previously mentioned depth 2 lower bound to an approximation lower bound. Thank you.
All right, so we have time for questions. We have one from Yoda Berry, who asks, even though your results are for approximating parity, is there anything they imply for exact computation parity?
Well, so it doesn't imply anything for exact computation of parity as far as upper bounds go. As for the lower bounds, lower bound on approximating parity also implies a lower bound on computing parity exactly. But I agree, it's an interesting open problem whether QAC0 circuits can compute parity exactly.
If anyone has a last question, you can ask now. Otherwise, I think the next thing is the coffee break, virtual coffee break. All right, then. Thank you, Gregory, very much for your talk. It's very interesting. I think next we're going to put up the directions to go to the coffee break.
So hello everyone. Welcome to the last session of the first day. So I think our two speakers, we will have 5 talks, and 2 of them are already here, and 3 of them still not seems here. If they are here, please raise your hand and we can add you. So we will start with Priyanka. Priyanka, you may share your screen. Hello.
Hello.
You may share screen. We still have 1 minute.
Okay.
So you can ask your questions. You should see there is a question answer in the bottom part of Zoom control, and you can ask your questions there. Okay. So after Priyanka, Andrew will take the stage. And I hope the other speakers will also appear meanwhile. Okay, we can start now. The first talk is Priyanka Mukhopadhyay. Yeah, it's a challenging surname, similar to mine, I guess. Okay, Priyanka, please.
Hello, everybody. Thank you again for allowing us to give a presentation on our paper. So today I'll briefly describe algorithms to reduce the C0 count for Clifford plus T circuits on NISQ architectures. This work has been co-authored with Vlad Kargiu and Michele Moshka from IQC and Sarah Mengli from Dalhousie University. So to motivate our problem, first let us quickly understand what a quantum compiler does. It takes a quantum algorithm and it outputs a quantum circuit. This circuit consists of some quantum gates, which are admissible by hardware constraints. Usually, these gates belong to some universal fault-tolerant gate set. For example, Clifford plus T is one such very popular gate set. It consists of the following single qubit gates, X, Y, Z, Hadamard, T, and phase gate, and their adjoints. And it has only one 2-qubit gate, the C0. Now, one of the constraints which is imposed by the hardware is the connectivity constraint, by which 2-qubit operations are possible only among certain pairs of physical qubits. This is usually represented by a connectivity graph. For example, this is a connectivity graph. There is a permutation which maps the vertices of this graph to the qubits. So if an edge ij exists between 2 vertices, then it implies that 2-qubit operations are possible between qubits pi I and pi j. These are some of the connectivity graphs of some of the architectures that we have considered in our paper. Now, one solution to this problem is to use swap gates, by which we move a pair of logical qubits to admissible physical positions. For example, suppose we want to implement a C0 between qubits 1 to 9, and we see that there are no direct edges between them. So what we can do, we can put swap gates in the path between 1 and 9, and then perform the C0 operation. Now, one swap gate is equivalent to 3 C0 gates, and each C0 gate imposes some additional noise. So now the question is, can we reduce the C0 count while respecting the connectivity constraints? So our algorithm is basically a slice and build algorithm. We first slice the input circuit and get subcircuits which do not contain Hadamard gate, and then we build or resynthesize these subcircuits. To do this, we use the circuit polynomial correspondence, by which we associate a phase polynomial and a linear Boolean transformation with every quantum circuit over the Clifford plus T gate set. We derive this correspondence as follows. We first initialize each qubit with path variables, the phase polynomial, which is represented as a set of monomials, which is usually called the parity terms, and their coefficients. So we initialize it as empty set. Then for each gate, we change the parity of each qubit according to some rules. And then we add appropriate coefficient parity terms to the phase polynomial. We have investigated two kinds of slicing in our paper. In the first method, we partition the gates of the input circuit based on the locality of Hadamard gates. For example, this is a circuit. So we kind of partition this circuit, excluding the Hadamard gates. Then we calculate the phase polynomial and linear transformation of the subcircuits. This is sufficient to represent these subcircuits which do not contain the Hadamard gates. In the second method, we first calculate the phase polynomial of the input circuit, and then we partition the parity terms in the phase polynomial according to the scope of the variables between Hadamard gates. This is due to the circuit polynomial correspondence. We calculate the linear transformation between consecutive Hadamard gates. So thus, after calculating these two terms, we can represent these circuits uniquely and we can resynthesize them. So now these circuits which do not contain the Hadamard gates are usually called the phase polynomial networks. So we have designed the phase polynomial network synthesis algorithm. So what is a phase polynomial network? It's a set. So given a set of phase polynomials, like given a polynomial, phase polynomial over an n-qubit circuit, the phase polynomial network is an n-qubit circuit over the C0 xt gate such that for each element Cf in this polynomial, the parity F appears before a gate in this set. So for example, this is a phase polynomial which is represented as a set. So we can represent it as a matrix. Each column is a parity term. The last row that represents the coefficient terms, and the second last row captures the bit flip variable. If we exclude the last two rows, then we get a parity matrix. So first we apply sequence of C0s equivalent to XOR operation on rows of this parity matrix such that each column has only 1, 1. So we do a reverse engineering procedure. If a column has only 1, 1, that implies the corresponding parity has been realized. Then we place a gate depending upon the coefficient of the parity term. These C0s are placed according to traversals in Steiner trees constructed in the connectivity graph. Now, what's a Steiner tree? Given a graph G with a weight function and a set S, which is a subset of the vertices of this graph, a Steiner tree is a minimum weight tree that is a subgraph of this graph G such that this set S belongs to the set of vertices of this tree. For example, suppose this is a graph and we have this set which is usually called the terminal nodes 1, 3, 8. Then this blue tree is the Steiner tree and all the non-terminal nodes here are called the Steiner nodes. Computing a Steiner tree is NP hard, but there are efficient heuristics to compute approximate Steiner trees. So after applying the phase polynomial network synthesis algorithm, we have this circuit which doesn't include the Hadamard gates. And if we place the parity terms, then we have a transformation that maps this xn plus 1 to xn to y1 to yn. But we require a transformation that maps to x1 dash to x2 dash and xn dash. Now, this transformation can be realized by a circuit on C0x, and we usually call it a linear, and this is a linear transformation. So let's look at an algorithm for synthesizing this circuit. This linear transformation is represented by a linear transformation matrix. This is an n cross n plus 1 augmented matrix. The rows are indexed by qubits. The first n columns, they represent initial path variables. The last column indicates bit flips. Now, given a linear transformation matrix, we apply some row operations which correspond to applying C0 such that A is reduced to identity. We again do a reverse engineering idea similar to Gaussian elimination. First, we look at the last column. If there is a 1, we flip it to 0 and place an X gate. Then we apply a series of row operations to reduce A to an upper triangular form. We transpose A and then we apply another series of row operations to reduce it to identity. Each such row operation corresponds to the application of C0 gates. Now, these C0s are placed according to traversals in Steiner trees in connectivity graph. Now, this concept of using Steiner trees has been previously used by two other groups, in two other papers. One is by Kissinger and Degren, another is by Nash, Khargyu, and Moshka. So let's look at a comparison of our work with their work. First, let's look at the linear transformation algorithm. Now, while reducing to upper triangular form, it so happens that we traverse the Steiner tree twice, while both these papers traverse 4 times. So we are able to reduce some C0 here. Now, while reducing it to identity, NGM20 uses templates and KDG20 uses a different recursive procedure. So the procedure which we use, that gives much less number of C0 gates. So we get further reduction in the C0 count. Now let's look at the phase polynomial network synthesis algorithm. So the way we flip the Steiner trees and drew the traversals in our algorithm, that ensures that all the parities are realized correctly. The phase polynomial network synthesis algorithm in NGM20, as it is described in the paper, does not realize all the parities in the circuit. So that's not correct. And KDJ20, the hint Steiner trees can be used. They don't explain how. While including the Hadamard gates, the NGM20 sketch how to use their phase polynomial network synthesis algorithm, which itself is not correct as it is written. However, we use a different partitioning of the circuit, and then we synthesize the circuits. Now we have implemented our algorithms on some benchmark and random circuits. These are the results on some benchmark circuits. So these are the architectures we have considered: 9-qubit square, 16-qubit square, Rigetti 16-qubit Aspen, IBM QX5, and Q20 Tokyo. The second column gives the number of qubits. These are the benchmark circuits. Now in the fourth column, we have given the overhead when we use swap template. That is, we use swap, then convert it to C0, then do some optimization. Then we get this kind of overhead in the C0 count. In the fifth and the sixth column, we give the overheads, which is obtained by our two kinds of slicing. The fifth column gives the overhead by using our first kind of slicing, and the sixth column gives the overhead when we use our second kind of slicing. In these benchmark circuits, we see that we have significantly less overhead compared to the swap template. Now, these are the results on some random circuits. So here the second column gives the number of qubits. The third column gives the number of C0s in the initial circuit. The fourth column gives the overhead when we use swap templates. The fifth column gives the overhead while using our first method of slicing, and the second column gives the overhead when using our second method of slicing. So we see like we have considerably less overhead in reasonable time. And also we have good scalability in the sense that as the number of C0s increases in the input circuit, the overhead doesn't blow up too much. So our algorithms have good scalability. These are further results on these IBM QX50 and Q20 Tokyo architecture. So to summarize my talk, we have developed algorithms that reduce C0 count while implementing Clifford plus D circuits on connectivity constant architectures. We use slice and build techniques. We use Steiner trees to resynthesize phase network circuits and linear transformation circuits. We obtain significant reduction compared to swap template, and our algorithms also achieve good scalability. Thank you.
Thank you, Priyanka. You have one question. Can you see the question?
In the chat?
It's in question answer. Let me say it. What is the idea behind selecting out Hadamard gates, and how is it that selecting out Hadamard is able to give us a lesser C0 count?
Okay, so this comes from this is due to the circuit polynomial correspondence. Now the circuit polynomial correspondence gives a sum over paths representation for every Clifford plus D circuit. But if the circuit doesn't consist Hadamard gates, if the circuit doesn't have Hadamard gate, then we have a one-to-one correspondence. Like if we have a circuit, we can have a sum over paths representation. If we have the representation, we can uniquely synthesize the circuit. But if we include the Hadamard gate, then given the circuit, we have a sum over paths form, but it's not the other way around. That's why we exclude the Hadamard gates and then take the sub-circuits which do not contain the Hadamard gates. Then we can compute the sum over paths form. And from that sum over paths form, we can uniquely resynthesize these circuits. So the Hadamards have been excluded only due to this reason. It doesn't contribute to reduction in the C0 count.
Okay, thank you. So we will continue with Andrew. Priyanka, can you stop the share, please? Yes. Thank you.
Thank you so much.
So before start, Andrew, I think one of speaker is still missing, and we might shift after Andrew, maybe Lee Hang, and then you can take stage earlier. Okay, we are now 3 minutes behind the schedule, and Andrew, please start. Thank you.
Okay, cool. Yeah, so Thanks for the introduction, Abuzar. So hopefully I can make up for a little bit of time because I will only talk for around 5 minutes or so. And also, excuse me if my voice is a little bit sore because I'm recovering from a cold. So please excuse that. So today I'll be telling you guys about my talk on the website on YouTube, and it will be on using power law interactions to implement a fast unbounded fan-out gate. So to start off, the state of quantum computing today, we have processors with intermediate numbers of qubits, such as Google's Sycamore chip that has 53. Unfortunately, these qubits have very low coherence times, and so they lose their quantum magic, so to speak, very quickly. And therefore, a priority for NISC-era practitioners is to implement their algorithms in as low depth as possible. So one way that they can do this is using this standard classical parallelism, which is that you take your circuits and you implement all gates that act on non-overlapping sets of qubits at the same time, for example here. And if you have circuits that act on n qubits, then the best improvement you can get using this parallelism is a factor of n. So another way you can improve it is to use multi-qubit gates. And these are gates that act on a constant fraction of the qubits in your system. So it's proportional to something times n. This includes, for example, Glober-Morver-Sorensen gates in trapped ions. And here you can get at most a factor n improvement as well. Now, both of these solutions by themselves are halfway decent, but as it turns out, we can be a little bit more ambitious and get a better solution to getting low depth circuits. And that's by combining these two approaches into what I call enhanced parallelism. So this enhanced parallelism, as compared to the vanilla classical parallelism, where you have gates acting on different qubits at the same time, it turns out that you can consider an alternate model where you can implement commuting gates that act on the same qubits at the same time. So for example, in this model, you could implement these 3 C0 gates, which are each controlled on a single qubit register, but with different targets, and implement them at the same time into this single multi-qubit gate. And this, this gate is rather special. It's known as the unbounded. It's known as the quantum fan-out gate. So specifically, it behaves as a singly controlled multiple target gate. So here would be the controlled not. And when we call it unbounded, we simply refer to the fact that the number of targets can be as large as the number of qubits in your circuit. And it turns out this unbounded fan-out is exactly the resource that you need to implement this enhanced parallelism. For the details, you can see my talk. And now the power of this unbounded fan-out, or this model, can be demonstrated with a simple example. So if you take the quantum Fourier transform, whose use I do not need to justify, is the standard way to implement it is to implement it in this log depth circuit, as shown by Waterson-Cleave. But it turns out using the unbounded fan-out, you can actually implement it in constant depth. And this was due to Hoyer and Spalek. Furthermore, you can implement arithmetic operations, such as modular exponentiation in constant depth as well. And these two factors combined means that you can implement a Shor's factoring algorithm using a shallow quantum circuit, provided you have some polynomial preprocessing with a classical computer. So this demonstrates the power of this model. However, the problem is with implement this in practice is that we are limited by hardware. And so specifically, if you consider Google's Sycamore chip, which is a 2D nearest neighbor architecture, then the fan-out time for this circuit, specifically the depth required to implement a fan-out, would scale polynomially in the system size. And so this would kill any speed up that you could hope to get using these constant depth circuits. However, there exists this alternative qubit architecture where you have more interconnected gates. And specifically, those are called power law interacting graphs. And these systems can be found in AMO, atomic and molecular and optical systems. And these include cold atoms and polar molecules. And it turns out, as we show in the talk, that there exists a protocol for implementing the fan-out gate very quickly using these power law interacting graphs. And as a corollary, we show that it is classically hard to simulate these power law systems, assuming that factoring is hard. And so this is a sort of a neat corollary of our fan-out protocol. And finally, we give a new technique for proving circuit depth lower bounds for restricted qubit architectures such as this 2D nearest neighbor grid. And in general, we show that the fan-out time, as well as the quantum Fourier transform time in these systems is linear in the system size. So with that, I'd like to thank my collaborators you see listed here. And I encourage you to look at my talk if you are interested.
Okay, thank you. So we still have 3 minutes. Is there any question? So I may ask one. So you mentioned about hardware limitations, but I guess is there also some limitations for any type of hardware? Is it correct? I mean, even you make some magic, etc. If you try to fasten, but still there should be some limitation, for example, when scaling or something.
Indeed. So, right, as you correctly suggest, you cannot instantaneously send information from one place to another. So there will always be this sort of overhead. And that will prevent you from doing, constant time algorithms because, it has to somehow scale with your system size. So what we're claiming to show is that there's, for certain systems, you can actually improve over this polynomial time scaling. And in particular, you can get some logarithmic scaling with your system size. And so this, for these power law systems, is an improvement over the nearest neighbor systems. So it's not as fast as constant time, but it's still faster than polynomial.
Okay, thank you very much.
Yep, thank you for that question.
So I think we can proceed, and Ryan is still missing. Ryan, are you around? Just say hello or raise hands, but if not, maybe Link Hank, are you ready to continue? Yeah, sure. He already shared. Okay, thank you very much. Now we are shifting. And now Lin Han Kong will continue. Okay, please.
Yeah, thanks for the introduction. I'm Lin Han from MIT, and today I will talk about constructing covariant quantum error correction codes using random circuits. This is joint work with Ziwen from Perimeter Institute. So quantum error correction code have been a hot topic in this field, and the main idea is to encode the logical quantum information into the subspace of a large physical quantum system, so that it will be robust against a noisy channel. And in our work, we will consider the erasure error, which erases a T of the subsystems in the physical system. And the code we consider is called covariant code. Basically, it means that it is some quantum error correction code with some symmetry condition. The more precise definition is that if a code is covariant with respect to some symmetry group G, it means that the encoding channel commutes with the group action. So if you apply the group action on the logical system first, and then do the encoding here, that's equivalent to doing the encoding first, and then apply the physical action. And furthermore, we'll assume that the physical action takes the tensor product form. It is a tensor product of unitaries on each of the subsystem in the physical system, physical quantum system. So why do we care about covariant codes? The most important aspect for the quantum information scientists is that such covariant code allows the logical gates to be implemented transversally, or in other words, in the form as a tensor product over each of the subsystem in the physical Hilbert space. And such transversal implementation does not propagate errors. So it has an advantage for fault tolerance, and it is very useful for constructing fault-tolerant quantum computing protocols. And covariant codes also arises in other important areas in theoretical physics, like condensed matter, quantum gravity, and reference frame quantum error correction. Well, covariant codes are nice, but they also have limitations. So there is a famous Isting-Newell theorem, which states that if a code is covariant with respect to a continuous group, then it cannot correct erasure errors perfectly. And furthermore, even if we do not ask for perfect error correction, there are some limitations for approximate quantum error correction code. And approximate codes the performance of approximate codes are often measured by these two quantities, which are called tri-error and worst-case error. They both measure the error rate of the code. And the generalized approximate Isting-Newell theorem states that if a code is covariant with respect to a continuous group, then there is a lower bound for the tri-error and the worst-case error if you erase one of the physical system. This means that the error rate cannot be decreased indefinitely, and there is a limit for this. And as for our results, we consider codes that's covariant with respect to U1 group. And the code encodes k logical qubits into n physical qubits. And basically, our result, we have an achievability result. We show that the U1 covariant codes generated by hard random charge conserving unitaries almost always saturate the lower bound that we have shown before. So this provides a construction for good covariant codes, and it also reveals interesting properties for such charge conserving unitaries. To be more precise, our construction has a parameter alpha, and in the large n limit, where n is the total number of physical qubits, if alpha is linear in n with the coefficient between 0 and 1, then we have shown that with high probability, the error rate of our random codes has such upper bound under the erasure of t qubits. So the high probability here means 1 minus an exponentially small amount. So it's a very high probability. And if we take this parameter a equal to 1/2, this saturates the worst case error, the lower bound for the worst case error exactly, and the tri-error up to a constant factor. So basically, our constructed code is the best possible error correction code we can have. One interesting thing to note is that although we have used hard random unitaries, it is sufficient to have two designs. Although two design without symmetry has been a widely considered topic, but if we pose this symmetry constraint, it is not clear if we could construct two designs efficiently. For future work, the most important thing is to generalize this into the SUD symmetry group because that's more relevant to the fault tolerance. Also, it's interesting to consider the decoding, and in general, it's interesting to consider random circuits with such symmetry. So thanks for listening.
Yeah, thank you for very concise and short presentation. Any question? So maybe I can try. This is not the topic I am feel comfortable, but so if I ask a kind of silly question, so what can be like implementation level? What would bring us your results?
So we're not sure about this, but one naive idea is to use a local, like 2-qubit random circuit. If you implement it many times, maybe it could converge to a 2 design. But such result was not known. Especially there was a paper by Iban Marvian maybe last year, and it states that this local circuit cannot converge to, are not universal for the global circuit with symmetry. So in other words, it does not converge to T design for arbitrarily high T. But still, it's not sure if 2 design could be obtainable this way.
Okay, thank you. So if there is no question, we may proceed. I think Ryan is still missing. Okay, if Yehui, if you are ready, maybe we can continue with your talk. Ling Hang, thank you. Maybe you can stop the sharing. So Yehui, quick. Are you ready? Okay, he also sharing. It seems.
Oh, give me 1 second.
Yeah, no problem. We have time.
Okay, I can start.
Okay. Thank you very much. And stage is yours. Please continue.
So good morning, good afternoon, or good evening, wherever you are. My name is Yihui Kwek. I'm a PhD student at Stanford University, and today I'll be talking about our joint work with Srinivasan Arunachalam and John Smolin, Private Learning Implies Quantum Stability. So the observation is that full quantum state tomography consumes a lot of samples, and by samples, I mean number of copies of the state that you need to prepare. And in a series of breakthrough papers, a couple of years ago, it was proven that we can exactly characterize this number of states up to a constant. And the number of states is exponential in the number of qubits. And obviously this is bad because it's an exponential. So a line of inquiry started by Scott Aronson and others was whether there could be other ways to learn quantum states that don't involve learning the full state. So rather than doing so, we could just consider learning the essential properties of each state. Namely, for each state, instead of learning the full density matrix, we could learn to predict trace rho E for any measurement E. And this is a very interesting line of inquiry at the intersection of computational learning theory and quantum mechanics. So Scott and others have proposed several learning models in this vein. And the point about these models is that they are often dramatically easier in terms of complexity. They have, instead of having exponential complexity, they have linear complexity, linear in the number of qubits. So our contribution today is to show that many of these essential learning models are deeply connected. So we're going to talk about a number of models, but just to talk about a general framework under which all these models can be cast, the critical observation here is that every quantum state rho defines a function, trace E rho. And here E is a 2-outcome measurement which outputs either accept or reject. And it's a point in the domain of this function. And this function evaluates to a probability of the measurement accepting on rho. And because it's a probability, so the function maps to the range 0, 1. So the question of learning an unknown state from a set of states then becomes the question of learning an unknown function from a set of functions. And this is exactly the kind of problem that computational learning theory deals with. So I'm going to talk about a bunch of learning models now. Unfortunately, I can only do so very briefly for each one. So the first learning model we're going to consider learns from noisy examples and where each example takes the form measurement, approximation of the measurement acceptance probability. And the first learning model is called PAC learning, where PAC stands for probably, approximately, correct. So in this learning model, you receive all your examples at once, and you do your learning on it, and then you eventually get a prediction algorithm that is able to predict the value of trace E rho for a new E with high probability after that. Instead of receiving all your examples at once, in an alternative model of learning called online learning, we could also consider receiving the examples sequentially. And here the learning model is that the learner is supposed to learn in an online fashion, which means that the learner predicts trace EI rho after receiving every example. And then every prediction receives some feedback. And then using this feedback, the learner refines his prediction algorithm. And the goal here is to minimize the number of prediction mistakes during the learning process. So there's another kind of learning model, shadow tomography, which is kind of a uniquely quantum learning model. In this learning model, you start off with a set of measurements, and there's also an unknown state. And then the goal is to use as few copies of the unknown state as possible to be able to predict trace EI rho to within epsilon error for all the measurements in the initial set of measurements. And finally, we could also consider a form of learning that consists of a communication game between Alice and Bob, where Alice has the state rho and Bob has the measurement E, and then Alice and Bob are separated by a long distance and are connected by a communication channel. And so Alice is supposed to send classical bits to Bob, and in fact, as few as possible until Bob is able to produce a good approximation of trace E rho. So we have several contributions in this paper. Our classical contribution is that we have established a web of implications between all of these learning models and combinatorial parameters. So even though we call them quantum learning models, they actually translate to learning models in the classical setting as well, because they correspond to learning real valued functions with noisy examples. And this is because of the translation that I outlined 2 slides ago, where the function that we're trying to learn is trace E rho mapping to between 0, 1. So this is a real valued function. And the noisy examples correspond to the fact that typically when we're trying to learn a quantum state, what we would be doing is we would be approximating the value of trace E rho by doing repeated measurements on the state. And this is how we get the examples. So some of these arrows were previously known for learning Boolean functions, but to our knowledge, this is the first work that is able to make these statements in the real valued learning setting. And in fact, not all of the implications that hold for learning Boolean functions actually go through for learning real valued functions. In particular, we proved a no-go theorem for the last arrow from stability to something known as approximate differentially private PAC learning. So we also have quantum contributions. Namely, there is this one particular combinatorial parameter called the sequential fat shattering dimension, which is kind of like the real value and online analog to the VC dimension, which is for learning Boolean functions, PAC learning Boolean functions. So we were able to bound the sequential fat shattering dimension of a set of interesting classes of quantum states, including K juntas, where the quantum states all lie in the same rank K low dimensional subspace, Gaussian states, and also states that have passed through some kind of noise channel. And because we were able to do so, we were also able to speed up shadow tomography when the unknown state comes from one of these interesting classes. So that's the end of my presentation. So we've shown this web of implications, and for future work, it would be really nice to see people use the implications we have now shown to port algorithms from one model to another. So that's all. Thank you.
Yeah, thank you very much. Is there any question? You can also raise your hand. Maybe, there is one. Okay, let me see. Okay, allow to talk. Yes, Han.
Yeah, can you talk a little more about your speed up for shadow tomography?
Oh, yeah.
What's and yeah.
Okay, so let me go back one slide. Yeah, okay, so the speed up here is that previously shadow tomography depends on several parameters, but one of the parameters, or its dependence on the number of qubits of the unknown state used to be n, which is like, so it's like linear the number of qubits of the unknown state. But in this case, we showed that shadow tomography has a complexity which is upper bounded by, in some cases, less than n. And the reason we were able to show this was because the sequential fat shattering dimension of certain interesting classes of n qubit quantum states can be less than n. So in fact, an upper bound on the sequential fat shattering dimension is n, but in certain interesting cases, it can be less than n. So we showed that the complexity of shadow tomography depends on this sequential fat shattering dimension. And by then upper bounding the SFAT dimension, we were able to speed up shadow tomography.
Thank you.
So any other question? I have a silly question. So you mentioned about 3 types of learning model. They are kind of incomparable, not like one is special case of others or something.
Yeah, so on the surface, they look as if they're incomparable, but the point of this work is to show that information theoretically, they are kind of connected. So learning in one model can sometimes imply learning in another model.
Okay.
Yeah, that's what these implications, these arrows actually show.
Okay, thank you. There is, if no question, thanks again, Yihui. Yeah,
no,
sorry. I think Ryan, is still missing. Okay. So I think we can close the session, but organizer already share a link for free virtual coffee is waiting you. You can click this link, and I think this coffee break still opens 50 more minutes. So, okay, thank you everyone, and see you tomorrow. Bye-bye.